Hi guys, in this video we will be starting a new topic which is called as the feedback amplifier. Now what is meant by feedback amplifier actually? It is an amplifier in a closed loop configuration. Closed loop means that the output signal is also fed back to the input terminal. That is, a portion of output signal is again connected back to the input signal, and that is called as a feedback amplifier. On your screen you can see the block diagram of a feedback amplifier. What all components do we have? First we have a source of the signal. This is the signal that you want to amplify. Okay, it is the input signal. Then we have comparator or mixer network. Just like control system in closed loop system, we have a summing element which we also call as comparator. So that comparator here is also called as mixer network. Why mixer network? Because it is mixing the two signal, the input signal and the feedback signal. Okay. So here we have shown the feedback voltage and the feedback current. The net signal is called as the input signal. Okay. So the signal going from the source terminal is called as the source signal, and the signal obtained after mixing of source and the feedback is called as input signal. Okay. Now this input signal is input to the amplifier. The amplifier has a voltage gain A. Okay, it might be voltage gain, current gain, depending upon the nature of amplifier. As I have told you earlier also, there are four kind of amplifier: voltage amplifier, current amplifier, transconductance amplifier and the transresistance amplifier. So here the amplifier has a gain of A. Then we have a sampling network. What is the purpose of this sampling network? Is to take out the output signal in order to feed it back to the input signal. Like in control system, what we say is, this is G, this is H, and we show like this. This we call as takeoff point. Okay. This takeoff point basically here is shown as a sampling network. So what is the purpose of sampling network? The purpose of sampling network is to take the output signal and send it back to the input signal. So sampling network samples the output signal in order to use it as a feedback. Then this signal output from the sampling network passes through the feedback network. Feedback network also has a gain of beta. Okay, so feedback gain is beta. What is the meaning of feedback gain? Suppose the voltage here is V0 and the voltage feedback is beta. So Vf by V0 is beta, like this. If current is fed back and we are taking current as the output, it is also beta. It depends on situation to situation what is the feedback signal and what is the output signal. Like the output can be voltage or current, same way the feedback can also be voltage and current. Based on this we can have how many combination? 4. Feedback voltage, output voltage, feedback current, output current, feedback current, output voltage, feedback voltage, output current. That way we can have 4 possible combination, which I have told: Vf, V0, Vf, I0, If, V0 and If, I0. And these will correspond to the 4 type of amplifier that I have already taught you: transresistance, transconductance, voltage and the current amplifier. Okay. So basically the relation between the output and the feedback signal is given by the feedback gain, that is beta. Okay. Beta is the feedback gain. Is it fine? Now basically in this topic we will be discussing more upon 2 things. One is the comparator or the mixer network, and the second one is the sampling network. These two things are very important to us, and we'll understand how to identify the feedback configuration based on sampling and the mixing network. Now first of all, if we talk about the sampling circuit. So sampling circuit, basically what it does is it takes the output signal, and I have told when we talk about output signal, what are the possibilities in case of output signal? Basically there are two possibilities, V0 and I0. So if V0 is fed back, that means you are taking the output voltage, then it is called as voltage sampling. That is, you are taking the sample of the output voltage. If I0 is fed back, that means you are taking the sample of current, then it is called as the current sampling. Okay. So there are two types of sampling, either voltage sampling or the current sampling. Now see, when we want to take the voltage, then this feedback wires are connected parallel to this RL. Okay, are you seeing this? This wire is connected parallel to RL, which means we are directly taking V0, and V0 is going into the feedback network. This beta is nothing but the feedback network. A is the forward path gain. So that is the representation of voltage sampling. And since you are taking parallel connection of the feedback network, the resistance will reduce in parallel. So output resistance with feedback is less than the output resistance without feedback. What is R0F? It is output resistance with feedback. R0 is output resistance without feedback. Since we are taking parallel connection of the feedback network, in parallel connection the resistance decreases, hence output resistance with feedback is less than the output resistance without feedback. See the second circuit. In the second circuit, if you see, in the feedback network we are not taking V0 but we are taking I0. That is why this wire is not connected parallel to RL, but it is connected in series like this. So the feedback network is connected in series with RL, or it will be called as the current sampling, because the feedback network input is your load current or output current R0. Since you have connected in series the effective resistance increases. So R0F is greater than R0. Okay. So if you are taking connection in parallel, the resistance will reduce. If you are taking connection in series, the resistance will increase. Okay. In parallel, what we are sampling? We are sampling the voltage. In series, we are sampling the current. So based on connection of the feedback network, we can tell whether it is current sampling or the voltage sampling. Okay. So there are two types of sampling. Next we talk about the mixer network. What is this mixer network? It basically combines the source signal with feedback signal. Okay. So mixer network always combines the source signal with the feedback signal. That is why it is called as the mixer, because it is mixing the two signal. Now again, when you are adding or subtracting two signals, there are two possibilities. What are the two possibilities? Either you are adding or subtracting the voltages, or you are adding or subtracting the current. Okay. Don't think of it as 4 combination, because I am also talking about addition and subtraction. So effectively there are 4 combination, but that will be taken care in positive and negative feedback. That is, when we are adding the two signal, it is positive feedback. When we are subtracting the two signals, then it is negative feedback. Okay. So what I mean to say is, when you are mixing the two signal, either both signals are voltages or both the signals are current. So there are two possibilities. One is called as voltage mixing and the other is called as the current mixing. The first block diagram shows voltage mixing. How? I told you the input to the amplifier is called as the input signal. This is your input signal. And the source connected is called as the source signal. And the output of the feedback network is called as the feedback signal. So once you combine the source and the feedback signal, then we get the input signal. Now let us apply KVL like this. So what I'll say? Vs minus Vi minus Vf equal to 0. So Vi is Vs minus Vf. So if you see, the source and the feedback voltages are subtracted to give me the input voltage. So I am saying it is voltage mixing. Now if you see, when voltages are added or subtracted, then it is your series connection. In series connection, resistance increases or decreases? Resistance increases. If resistance increases, RIF is greater than RI. What is RIF? It is input resistance with feedback. What is RI? Input resistance without feedback. Okay. See the second case. Here II is the input current, IS is the source current, and IF is the feedback current. Now apply KCL. This is IS, this is II. So I'll say IS minus IF is II. Again, to obtain the input current, we are subtracting the source and the feedback current. That is why it will be called as your current mixing. But if you see, this is an example of parallel configuration, because currents are added or subtracted only in parallel, not in series. In parallel, what happens? The resistance reduces. So that is why RIF is actually less than RI. Okay. And whenever the source and the feedback signal are subtracted, it will be termed as the negative feedback. What is the meaning of negative feedback? That the feedback signal is reducing the effective value of the input signal by getting subtracted from the source. See, if there was no feedback, the input signal will be same as the source signal, but due to feedback signal, the input signal is reduced, and that is basically called as the negative feedback. Okay. So we will see why do we go for negative feedback later on, but just remember, when the source and the feedback signal are subtracted, then it is termed as the negative feedback. Next, let us talk about the closed loop gain of an feedback amplifier. Now there are two possibilities in feedback, either a minus sign or a plus sign. Minus sign means negative feedback. So first let us talk about negative feedback. This is the feedback signal XF. It is feedback gain multiplied by the output signal X0. Then what is the input signal? I told you input signal is combined effort of the source signal and feedback, but we are taking minus sign only. So XS minus XF, okay, or XS minus beta X0. Now this Xi is getting as an input to the amplifier. So you can say output of the amplifier is gain multiplied by input, that is A xs minus beta x naught, that is axs minus a beta x naught. So if you take both the terms on the left hand side, x naught into 1 plus a beta is equal to axs. So x naught over xs is a over 1 plus a beta. Now in case if there is no feedback, if there is no feedback, you can say beta equal to 0. In that case, the gain would be equal to A. This is called as your open loop gain. This you can compare with the control system. There the open loop transfer function is represented by G. Here we are representing it by A. And this function is called as closed loop gain. So you can say that the gain with feedback is open loop gain by 1 plus a beta. Okay. So this will be less than A. This value will come out to be less than A. That means by the use of negative feedback, the gain reduces. Okay. So we are using negative feedback, and in that feedback the gain is being reduced. So if you want to represent the feedback, the effect of feedback in decibel, then you will write 20 log on the base of 10 gain with feedback over gain without feedback. So how much will it come out to be? 20 log 10, 1 over 1 plus a beta. So that is the effect of feedback in decibel. But always remember, by the use of negative feedback, the gain reduces. Now suppose I take the other possibility, that is with a positive sign. We know that xf was beta x naught. But when we talk about input signal, instead of subtracting the source and feedback signal, the signals will be added. So it will become xs plus beta x naught. Now this xi is input to the amplifier. So x naught will be a xi. So it is a into xs plus beta x naught, or you can say a xs plus a beta x naught. So you will write x naught into 1 minus a beta is equal to a xs, which means x naught by xs is a over 1 minus a beta. Again without feedback. Without feedback, what is the gain? The gain is equal to a. But with feedback, the gain is a over 1 minus a beta. So if you see the denominator, the term in the denominator is actually less than 1. So this value will come out to be greater than a. Because the denominator is less than 1, the overall value will be greater than a. So it means that in positive feedback, the gain of the amplifier increases. In negative feedback, the gain reduces. In positive feedback, the gain increases. So if I want to find the effect of feedback in decibel, as I told earlier, it will be 20 log on the base of 10 mod of gain with feedback upon without feedback. So 20 log on the base of 10, 1 over 1 minus a beta. Okay, that is called as your effect of feedback in decibel. Is it fine? So just remember one thing, in negative feedback the gain reduces, in positive feedback the gain increases. Okay, that much you have to remember for now. Now let us talk about another term, that is gain sensitivity. Now gain sensitivity represents how much does the gain of feedback amplifier is stable or it remains constant with respect to the external changes. So gain sensitivity represents how much stable is the gain of closed loop amplifier or feedback amplifier with respect to external changes. That is, even if we change small factors like temperature, pressure, humidity, all these factors should not affect the gain of the closed loop amplifier, and that is called as your sensitivity. Okay. So we know that the gain with feedback is, in negative feedback it is A over 1 plus A beta. So why I am taking negative feedback? Because negative feedback is used in amplifier, whereas positive feedback is used in oscillator. And right now I am only talking about amplifier, so I am taking negative feedback. Now if you differentiate this feedback gain with respect to open loop gain, so we will apply quotient rule. Derivative of numerator is 1 multiplied by denominator, minus derivative of denominator is beta multiplied by numerator, whole divided by denominator square. So it is 1 over 1 plus A beta whole square. Okay. Now when we talk about sensitivity, we write it like this: fractional change in closed loop gain divided by fractional change in open loop gain. The same thing you will study in control systems also when we talk about sensitivity of a control system. So we are taking fractional change and not the absolute change. So it is A by AF into DAF by DA. A is A, AF is A over 1 plus A beta into DAF by DA is 1 over 1 plus A beta square. So this sensitivity is 1 by 1 plus A beta, which is less than 1. It means that fractional change in closed loop gain is less than fractional change in open loop gain. And if you multiply by 100, fractional change can be converted to your percentage change. So percentage change in closed loop gain is less than percentage change in open loop gain. So it is a beneficial thing for us. Why beneficial? Because even if the open loop gain changes due to environmental effect, the closed loop gain will change by small amount or it will remain almost constant. Okay, that is what we desire, that the closed loop gain should not change with respect to environment even if the open loop gain changes. Now we define another term which is called as D sensitivity. D sensitivity is 1 over sensitivity. It is 1 plus A beta. Okay. Just remember this term D sensitivity. It is reciprocal or reverse of your sensitivity. Okay. So what is the purpose of defining sensitivity? We want to know how will the closed loop gain of the amplifier will change if open loop gain changes due to certain factor. To study that, we are defining the term sensitivity. Now let us understand why we go for negative feedback when we know that negative feedback reduces the gain. Okay, we know that thing. So then why we are going for negative feedback? Okay. So the first reason is frequency distortion. What is this frequency distortion actually? When we were studying BJT, I told you when we were studying frequency response that there are capacitances involved in the amplifier, due to which we saw that the frequency response was somewhat like this. Like this. Okay. Which means the gain was varying with frequency at low frequencies and high frequency. The gain was varying with the frequency. That means there will be frequency distortion, or the amplification will depend on frequency. Why I am saying distortion? Suppose there is a signal which contains multiple frequencies. Multiple frequencies means multiple sinusoidal signal with different frequency. Suppose there is a square wave. A square wave can be expressed as Fourier series. So it will have multiple harmonics or multiple frequencies. Now since gain is a function of frequency, each frequency or each component will have different gain. If they all have different gain, the shape of the output signal will not be identical to the input signal, and that is called as the distortion or frequency distortion. If all components do not have the same gain, the shape of the output signal cannot be identical to the input signal. Okay. So by the use of negative feedback, this frequency distortion is reduced. So that is the first reason why we are going for negative feedback. Then the second is non-linear distortion. It means if your network contains certain non-linear element like diodes and BJTs, then due to non-linearity of such element, the shape of the signal will change, and that is called as non-linear distortion. So non-linear distortion with feedback is equal to non-linear distortion by 1 plus A beta. So it is also reduced. What is non-linear distortion? The change in the shape of the signal due to non-linear nature of the devices used in the network is called as non-linear distortion. The third factor is noise. Noise is nothing but a high frequency unwanted signal that is introduced in the system either externally or internally. Okay. Due to environment or any other external components also, the noise can be induced in the system. So that noise also is reduced due to feedback. So it is open loop noise by 1 plus A beta. Okay. That means the noise in the output signal will be reduced if you are using a feedback amplifier rather than the open loop amplifier. Okay. And the last factor is your bandwidth. I told you what is the bandwidth. Bandwidth is nothing but the range of frequencies over which the gain almost remains same is called as bandwidth. Okay. I have told you in negative feedback the gain is reducing, but we know one thing, that the product of gain and bandwidth always remains constant. So suppose earlier the gain was high like this. Then what was the bandwidth? This was the bandwidth. Now the gain has reduced. So what should happen to the bandwidth? The bandwidth should ideally increase. If the gain reduces, the bandwidth should increase. Okay, this is the new bandwidth, this is the old bandwidth. So gain multiplied by bandwidth should be constant, since gain in feedback is less than gain in open loop. The bandwidth in feedback is greater than the bandwidth in open loop. Okay, so by reducing the gain in negative feedback, we are increasing the bandwidth. Okay, so if we summarize the effect of negative feedback, all type of distortion decreases, noise decreases, and bandwidth increases. The gain also reduces. Okay, so that is why we use the negative feedback. So if I summarize what I have covered in this video, I have told you about the basic of the feedback amplifier, why we are using feedback amplifier and what is the block diagram, and then we have seen the two important components of a feedback amplifier, that is the sampling network and the mixer network. In both I have told you there are two possibilities: voltage, current, voltage, current. And then I have told you, based on these two choices, there are four possible combinations, each corresponding to one type of amplifier. Then we saw the gain in the closed loop configuration is A over 1 plus A beta for negative feedback and A over 1 minus A beta for the case of positive feedback. Okay. Then we saw sensitivity. For negative feedback it was 1 by 1 plus A beta square, and it represented the percentage change or the fractional change in closed loop gain with respect to fractional change in open loop gain, and D sensitivity was 1 by S. And then I have told you the effect of negative feedback, that it reduces noise and distortion and increases the bandwidth. Okay, so in the next video we will cover different type of feedback configuration. As I have told you, there are four possible combination. So we will cover each and every combination, but we will start in the next lecture. Thank you. Hi guys, in the last video I introduced to you the concept of feedback amplifier. So I told you what is a feedback amplifier. It is a closed loop amplifier configuration in which a fraction of output signal is fed to the input terminals. Okay, so I showed you the basic block diagram of a feedback amplifier, and in the block diagram we saw that there are basically two components that are very important. One was the mixer network that was used at the input terminal, and the other one was sampling network, okay, that was connected at the output terminal. And then we saw that even in the mixer network we can mix either voltage or current. Similarly, in the sampling network, you can either sample the output voltage V0 or you can sample the output current I0. That is what we saw in the last video. And then we saw that the gain after feedback was A over 1 minus A beta for positive feedback, and it was A over 1 plus A beta for the case of negative feedback. Okay, that we saw. Then I told you about sensitivity. which is the ratio of percentage change in the closed loop gain with respect to percentage change in the open loop gain? It was 1 over 1 plus A beta square. So in negative feedback, the sensitivity reduces, and due to reduction in sensitivity, the closed loop gain does not vary much with respect to the change in open loop gain. And the desensitivity was equal to 1 by sensitivity. Then I told you, due to negative feedback, distortion and noise both decrease, whereas the bandwidth of the system increases. Okay, so this we saw in the last lecture, and I also told you, based on configuration of mixer and the sampling network, we can have 4 possible combination. Okay, so we can talk about 4 possible combination based on which quantity is being sampled and which is being mixed. So what are the 4 combination? The first one is called as series shunt feedback. Series is representing here the mixing network and shunt sampling. If you are mixing in series, it means you are talking about the voltage. If you are sampling in parallel, it means you are talking about V0. Okay, that means at the output also you are taking voltage, and at the input also you are taking voltage. You can also write it like this: voltage series feedback. But when you write it like this, the first term will always represent sampling, that we are sampling the voltage, and the second term will represent mixing. So if you write like this, series shunt, the first term is mixing, second one is sampling. If you like voltage series, then the first term is sampling and the second one is mixing. Similarly, let me ask the second one. Suppose I write shunt series feedback. Then shunt means it is representing mixing. Mixing in parallel, so it is current. Series means sampling in series, it is current. So what you will write? Current is being sampled and it is mixed in shunt, so current shunt feedback. Okay, so these are the 2 possible cases. Let me represent other 2 also. Okay, so suppose the third one I ask is series. The first series represents mixing. The second series sampling. So what you will say? Sampling is current and then mixing is series. So current series feedback. Okay, and the last one shunt feedback. So shunt is mixing. Mixing is shunt means current. Sampling is shunt means voltage. So it will be what it will be called as? It will be called as voltage shunt feedback. In the second naming, always remember that this represents sampling and this represents mixing. So that is how we have 4 configurations for the feedback amplifier based on the quantity being sampled and the quantity being mixed. So from this lecture onwards, we will be studying about these 4 configurations. So in this lecture and the next one, I will explain you the all 4 configuration. So let me start with the first one. The first one is the series shunt feedback. So let me again write down. Series means this is mixing. Mixing in series means voltage. Shunt is sampling. In parallel, which quantity do we measure? Voltage. So feedback is voltage and output is also voltage. If input and output both are voltage, it is voltage amplifier. The voltage amplifier is also called as voltage controlled voltage source. So now see, there are four names for the same thing: voltage amplifier, voltage controlled voltage source, series shunt feedback, or voltage series feedback. You can write this using four names. See, in the forward path we have a voltage amplifier having a gain AV. So in the forward path we have a voltage amplifier. In feedback path we have a voltage gain of beta, and the feedback voltage is connected in series with the supply voltage, and the sampling is in parallel to the load resistance. Okay, because sampling is shunt whereas the mixing is series. So at the input side we are connecting in series, but at the output side we are connecting in parallel. Now basically the voltage amplifier has a very simple circuit. If I talk about the circuit of forward path, this is the input resistance. Across this resistance I take input voltage Vi. Then we have a dependent voltage source in a voltage amplifier AV into Vi in series with the output resistance R0. Okay, so that is simply the voltage amplifier that I have shown in the forward path. Now this feedback voltage Vf, since feedback factor is beta, it is beta V0, because see, the input to the feedback path is V0 and the output of the feedback path is Vf. So Vf is beta V0. This beta is called as feedback factor. Now what you have to do in order to draw the complete circuit, you will show like this: Vs in series with a dependent voltage source which is Vf. What does it depend on? Vf depends on V0. Then I'll replace the voltage amplifier by input resistance Ri and a dependent voltage source AV Vi. What is Vi? Vi is the voltage across resistance Ri, and then it is the load resistance RL across which we take the voltage as V0. So I'll show the voltage here as Vi. So if you apply KVL, what you can tell about Vi? You will say Vs minus Vi plus, sorry, minus plus I have marked opposite. It is like this. Okay, from here I am taking the polarity, minus beta V0. So Vi will become Vs minus beta V0. And if you apply voltage division in this loop, you can say that V0 is the voltage source is AVVI into the factor of voltage division RL by R0 plus RL. So AV Vs minus beta V0 RL over R0 plus RL. So you can say V0 is AVVs RL over R0 plus RL. Okay, minus what it will be? AV beta RL over R0 plus RL into V0. Take the terms containing V0 on the left hand side. This will be the relation. Now what I'll do is I'll consider this term as AVL. This I explained to you in BJT. When we consider the effect of load resistance, then the effective voltage gain is written as AVL. So V0 is AVL. This term multiplied by this is also AVL. 1 plus AVL into beta into Vs. So what is the gain? Gain is AVL over 1 plus AVL beta. The same relation we derived using the closed loop system, that is the voltage gain. Okay. Even if you want, you can also consider the source resistance Rs. Okay. If you consider the source resistance Rs, then there will be another term of voltage division between Rs and Ri. So what I mean to say here is, suppose you consider a source resistance here. Suppose this is the source resistance. Then Vi will have another term, which will be Ri over Rs plus Ri. This voltage will be divided into two resistances, because earlier the entire voltage was appearing across Ri, but now it will be divided between Rs and Ri. So what we will have is, we will have another term Ri over Rs plus Ri. Ri over Rs plus Ri. And combining these three factors AV, RL and Ri, these three terms can be called as AVS. Okay, that is the overall voltage gain. Remember, in BJT amplifier I told you about the three voltage gain, AV, AVL and AVS. So the same thing I am telling here, you can represent the overall voltage gain by AVS. Okay. Now the other thing that I need to find out is the input resistance. The effective input resistance we want to find out. Okay. So suppose this is the circuit containing Rs also. This current is the input current. So if I apply KVL in this loop, what you will write? Vs equal to IIRS plus IIRI plus beta V0. Okay. Now how you can write V0? V0 is AVS over 1 plus AVS beta Vs. Okay. Take the terms containing Vs on the left hand side. 1 minus AVS into beta over 1 plus AVS beta. IIRS, IIRI. That means Vs. If you take the LCM is 1 plus AVS beta. So it will become 1 over 1 plus AVS beta IIRS plus IIRI. So Vs will be IIRS into 1 plus AVS beta plus IIRI into 1 plus AVS beta. So effectively the input resistance does not consider source resistance. I have always told you, when finding the input resistance, always ignore Rs. So this term on the right hand side will be called as RIF, that is input resistance with feedback. Okay, that is input resistance multiplied by 1 plus AVS into beta. So that is the overall gain. Okay, sorry, the overall input resistance. Is it fine? Next term that I need to find out is the output resistance. Okay. So if you want to find out the output resistance, then what you need to do is, see this. Okay. This current is I0. First of all, when we are finding the output resistance, we do not consider the load resistance RL. Always remember, you will not consider the load resistance RL. So if you apply KVL in the loop on the right hand side, what you will say? AV VI is equal to I naught R naught plus V naught. Okay, but we don't consider RL. AV VI equal to I naught R naught V naught. How you will write V naught? First of all, let me write down VI. 1 minute. How will I write VI? VI is simple. Vs minus beta V naught into a factor of voltage division. How I have written this? See. In the input loop, what is the total voltage? The total voltage is Vs minus beta V naught. Okay. And this voltage is being divided in two resistances, Ri and Rs. So what is the voltage across Ri? The total voltage into a factor of voltage division. And what about V naught? Or leave it like this only. Just write here AV Vs minus AV beta V naught Ri over Ri plus Rs equal to I naught R naught plus V naught. Okay. So now what you will do now is AV Vs. Okay. 1 minute. Sorry. There will also be a factor of Ri over Ri plus Rs here. So what I'll do is I'll combine these two terms, or let me call as AVS. Okay, this term minus AVS beta V naught I naught R naught plus V naught. Collect the V naught terms on one side. Now if you make it just V naught, you will have to divide it by 1 plus AVS beta. So the term with I naught is called as output resistance with feedback. It is divided by a factor of 1 plus AVS beta. So what you can say? R naught F is less than R naught. Okay. Now, what is the best way to remember this? The gain becomes AVS over 1 plus AVS beta. So the gain reduces. Bandwidth. Bandwidth becomes original bandwidth multiplied by 1 plus AVS beta. So bandwidth increases. Then the third thing, it is a voltage amplifier, right? Series shunt feedback represents voltage amplifier. If you refer to the earlier lecture about the 4 type of amplifier that I have taught you, I have told the input resistance must be high and output resistance must be low. In order to increase the input resistance, multiply it by a factor of 1 plus AVS beta, and in order to reduce the output resistance, divide it by a factor of 1 plus AVS beta. So input resistance will increase and output resistance will decrease. That means by the use of feedback, we are able to satisfy the requirements that we had set earlier for the amplifier. We are able to satisfy the requirement of the input and the output resistance. Okay. Moving on to the next one, the next feedback is called as shunt feedback. So the first shunt represents mixing. Mixing in parallel means current. The second shunt sampling. Sampling in parallel means V0. Okay. So that means here the feedback quantity is current and the sampled quantity is voltage. So when we talk about the feedback factor, it will be IF by V0 is beta. What will be the unit? The unit will be mho or Siemens. Current upon voltage is mho. Now since the input we have current and the output we have voltage, what kind of amplifier is it? It is trans resistance amplifier. Okay. So trans resistance amplifier means it is converting current to voltage. So the input side we have current and the output side we have voltage. Okay. Now see the basic structure. We have the source current and in parallel we are having the feedback current IF. The remaining current will be input to the trans resistance amplifier written as II. But sampling is done in parallel with the output terminal. So sampling is V0. Now what is the circuit of this trans resistance amplifier? If I just draw the circuit of this amplifier, we have input resistance on the left hand side, but we are taking the current of this resistance. Then we have a current controlled voltage source RMII in series with the output resistance. So basically it is a trans resistance amplifier. What is it also called as? It is also called as current controlled voltage source. Okay. Trans resistance amplifier is also called as current controlled voltage source. Okay. So now our objective in this amplifier also is to identify the gain, the input resistance and the output resistance. So let us draw the model. First I will draw the supply current IS. Now if we have source resistance as well, it will have a resistance RS in parallel to IS. Then there will be a dependent current source going downwards, which is IF, which is equal to beta V0. And then I will replace trans resistance amplifier by its equivalent circuit. So I will show RI and the current in RI is II. Then we will have a dependent voltage source RM into II in series with output resistance R0 and then the load resistance RL. The voltage across load resistance will be V0. Okay. So now the first objective is to find the voltage gain. So in the right hand side, if you apply voltage division, you will say V0 is RMII into RL over R0 plus RL. Now how to find this II? Basically there are two current sources in parallel, IS and IF, and they both are in opposite directions. So the net current is IS minus IF. And if you want to find II, there are two resistances in parallel, RS and RI. So you will have to apply current division. I net into RS by RS plus RI. Okay. So what is II? IF is how much? Beta V0 into RS over RS plus RI. Okay. So now when you substitute it in the expression for V0, it is Rm into RL over R0 plus RL into RS over Ri plus Rs into Is minus beta V0. If you club these three terms, I will write it as RMS Is minus beta V0. Now collect the terms containing V0 on left hand side. 1 plus RMS beta RMS into Is. So V0 by Is, that is the gain. It is RMS over 1 plus RMS beta. So RMS is the overall gain in absence of any feedback. If the beta was 0, then the gain would have been RMS. But due to presence of feedback, the gain is reduced by a factor of 1 plus RMS beta. Okay. So that is the expectation from negative feedback, that the gain must reduce. Now the next objective is to find the input resistance. How do you find input resistance? Basically, what I'll do is, I will write this voltage as Vi. So if I apply nodal, what I'll say? Is is the incoming current, beta V0 is outgoing. So Vi by Rs plus Vi by Ri. These two are also outgoing current. Okay. This current and this current is outgoing current. Now how you will write V0? V0 will be RML into Is. Okay. So how I am writing RML? I am using RML because when we are finding the input resistance, we don't consider Rs. Don't consider Rs in gain while finding input resistance. Is my point clear? This I have told you multiple times, that when you are finding the input resistance, we don't consider the source resistance, and that is why the gain instead of RMS is becoming RML. So this is Is over 1 plus RML beta Vi over Rs plus Vi over Ri. Now this will be Is Vi Rs over 1 plus RML beta plus Vi Ri over 1 plus RML beta. So the input resistance with feedback becomes Ri over 1 plus RML beta. So what you can say? The input resistance is less than its open loop value. Earlier the input resistance was higher, but now it has reduced. Why it has reduced? Because you are connecting it in shunt. Whenever we are connecting in shunt, the resistance must reduce. The last term that we need to find is your output resistance. Okay. So we wish to find the output resistance. How will you find it? We will consider a current I0 here. So if I apply KVL, I'll say RMII is I0 R0 plus V0. Don't consider RL when you are finding the output resistance. Now how do you write II? II was obtained by applying current division in the net value of current. This was the net current. See, I wrote here, this is the net current. and we applied current division. So RS over Ri plus Rs. So it is Rm Rs over Ri plus Rs into Is minus Rm Rs Ri plus Rs beta V naught I naught R naught plus V naught. Now this term Rm Rs over Ri plus Rs I will write as RMS beta V naught I naught R naught plus V naught. Collect the term containing V naught on one side. Okay. Now divide it by the coefficient of V naught. What you will get? Okay. So this term in product with I naught is called as output resistance with feedback. It is R naught over 1 plus RMS beta. So it is less than R naught. Again, because output is in shunt, the output resistance has reduced. So now what you have to remember, due to negative feedback, the gain will reduce. It will be RMS over 1 plus RMS beta. Since both are in shunt, input and output, both resistances will reduce. But while taking input resistance, we will take RML, and while taking output resistance, we will take RMS. Because while calculating input resistance, we ignore source resistance, and while calculating output resistance, we ignore load resistance. So if I summarize what we have covered in this video, I have told you first of all about series shunt feedback, which is also called as what? Voltage series feedback. It is voltage amplifier. So gain reduces, input resistance increases, output resistance decreases. The second one was shunt feedback or voltage shunt feedback. This was your trans resistance amplifier. Okay, here the gain reduces, input resistance decreases, as well as output resistance decreases. Okay, so we have covered 2 configurations out of 4 in this video. In the next lecture, I will tell you about the 2 more configuration, and then we will talk about how to identify which configuration is being used in a particular network. Okay, that we will cover in the next video. Thank you. Hi guys, in the previous video we started with the configuration of the feedback amplifier, and as I told you there were 4 configurations, out of which we covered 2 configurations in the previous lecture. The first one that we covered was series shunt feedback, which is also called as voltage series feedback. Or voltage amplifier. Okay, in this I told you that the gain of the amplifier became AVS over 1 plus AVS beta. Due to series connection at the input side, the input resistance became 1 plus AVL beta. Here I will take AVL because I have to ignore RS while calculating input resistance. Due to shunt connection at the output side, the output resistance reduces 1 plus AVS beta. Remember, while computing output resistance, you have to ignore RL, and here you have to ignore RS. Okay, this thing you always have to remember. The second thing that we covered was shunt feedback, or we can call it as voltage shunt feedback, or it was also called as trans resistance amplifier or current controlled voltage source. Okay, here the gain become, or trans resistance becomes, RMS over 1 plus RMS beta. Input resistance became RI over 1 plus RML beta. Due to shunt connection it reduced, and at the output also we have shunt connection, so it also reduces. So both the resistance will be reduced. In this video we will cover the other two configuration, that is series as well as the shunt series. So the first, let us start with series. What you will call it as? This is the first term represents mixing. So when you are mixing in series, you are basically mixing voltage, and when you are sampling in series, it means you are sampling current. So what you can call it as? Current series feedback. And since at the input side we have voltage and at the output side we have current, it will also be called as the transconductance amplifier, which is called as voltage controlled current source. Mixing is always done at the input side. So at the input side we are considering voltage, but at the output side we are considering current. So it is converting voltage to current, hence voltage controlled current source. Now see the block diagram. In the forward path we have a transconductance amplifier having a transconductance GM. Then its output is connected to RL, and we are taking feedback in series with RL because it is the series feedback. Okay, if you see, we are taking in series. Then this is the feedback factor beta. Beta is called as your feedback factor. Now mixing also has to be done in series, that is why this feedback voltage is in series with supply voltage, and their mix or the total value is acting as the input voltage to the transconductance amplifier. Now what is the equivalent circuit of transconductance amplifier? We have input resistance first of all. This input resistance will have a voltage Vi across it. Then we have a current source because it is voltage controlled current source. The current source is GM into Vi in parallel with the output resistance R0. Now if you connect this transconductance amplifier in the feedback configuration, how will the equivalent circuit look like? So let me also show the source resistance Rs, then the supply voltage Vs. The feedback voltage will be represented as a dependent voltage source, which is Vf, also equal to beta I0. Okay, because here the input term is I0, we are connecting in series, but the output of the feedback configuration is Vf. Then we will have the input resistance of transconductance amplifier Ri. This is Vi. Then a current source Gm Vi. This will be in parallel with R0, and then at the output we have the resistance RL, and the current in RL will be I0. So this feedback voltage depends on the current flowing through the output resistance of the load resistance RL. Okay. So always remember the term containing the feedback will be represented as a dependent source. Now what are our objective? Our objective is to find three things: gain, input resistance, and the output resistance. So first let us talk about the gain. How you will write I0? I0 I will write as GMVI into R0 by R0 plus RL, that is using current division. But it depends on VI. How to find VI? See, suppose this current is II. How you will write II? II is the total voltage. What is the total voltage? Vs minus beta I0. There are two sources which are in opposite polarity. That means they will be subtracted. So Vs minus beta I0. Now this is the total voltage by total resistance. The total resistance is Rs plus Ri. So what is Vi? II into Ri. So Vs minus beta I0 into Ri over Rs plus Ri. Now this value of Vi can be substituted in the I0 expression. So what I can say? I0 is Gm Vs minus beta I0 Ri over Rs plus Ri into R0 over R0 plus RL. Now this factor of current division, this is of voltage division, and this Gm, I will combinedly write it as GMS, that is overall transconductance. Okay. Now take the term containing I0 on one side, on the left hand side. It is equal to GMS into Vs. So what is the overall transconductance? GMS over 1 plus GMS into beta. If there was no feedback or beta was 0, then the overall transconductance would be GMS. But due to feedback it becomes GMS over 1 plus GMS into beta. What is this GMS? GMS is the open loop transconductance multiplied by the factor of voltage division multiplied by the factor of current division. Okay. Now the next term that we have to find is the input resistance. First of all, let me ask you, what do you expect in the input resistance? It is series feedback. That means at the input as well as at the output terminal we have series connection, and in series connection we know that the resistance increases. So our expectation is that at both the input as well as the output resistance should increase. So if I write the input resistance, how will I write it? See, if we apply KVL in this loop, what I will say? Vs minus beta I0 is equal to II into Rs plus II into Ri. Now this I0, how you will write I0? beta GML into Vs. Why this GML? Basically, while finding RIF, ignore RS. Now if you ignore RS in this transconductance, the only factor that will remain is the current division R0 by R0 plus RL. So here GML I mean to say is GM into R0 by R0 plus RL. That is your GML. IIRS plus IIRI. Okay. Sorry, not only GML, GML 1 plus GML into beta, because it is closed loop. So if you take the LCM, you will get Vs over 1 plus GML beta IIRS plus IIRI. Take this 1 plus GML beta on the right hand side. Ri multiplied by 1 plus GML beta. That means the effective input resistance is Ri multiplied by 1 plus GML beta. So as I told you earlier also, due to series connection, the input resistance will increase. Now let us talk about the next term, that is your output resistance. Now while writing the equation for output resistance, what I will do is, I will say that this voltage is V0. Okay. So if I apply KCL at this node, there is one incoming current GMVI and there are two outgoing current. So GMVI will be equal to two outgoing current. The current in R0 is V0 by R0, current in RL is I0. Okay. Now how to write this VI? If you want to write VI, you will have to apply voltage division between RS and RI. This is the net voltage, Vs minus beta I0. That is the total voltage at the input side. And we will apply voltage division. That is your VI. This we wrote earlier also. Now what I will say is GM into this factor is GMS. Vs minus beta I0 is V0 by R0 plus I0. Take the term containing I0 on the right hand side. I0 1 plus GMS beta. Now divide it by 1 plus GMS beta. That means the output resistance with feedback is R0 into 1 plus GMS beta. So as predicted earlier, the output resistance also increases due to series connection on the output side. Okay. Since we have series connection on both the sides of the amplifier, both the resistances are increasing. Moving on to the last feedback configuration, we have shunt series feedback. Okay. So shunt series feedback, shunt means this is representing the mixing. If we are mixing in parallel, what we are mixing? Current. Series, it represents sampling. If we are picking any quantity from series, what we will pick? Current. So you can also call it as current shunt feedback. This can also be called as current amplifier. Okay. This will be your current amplifier. Now, This can also be called as one more thing, current controlled current source, because at the input and the output side we have current. Now see the block diagram. In the forward path we have a current amplifier. In the feedback we have a feedback factor beta. Okay, feedback factor beta. Now we have connected at the input side, we have connected in shunt, and at the output side we are taking the output current, or you can say series, and this is in shunt. Now what is the equivalent circuit of a current amplifier? First of all, I will have a input resistance Ri. It is a current amplifier, so what we will see in Ri, I will see the current Ii. Then we have a dependent current source Ai into Ii in parallel with a output resistance R0. Okay. Now what we will do is, we will represent, or we will replace this current amplifier by its equivalent circuit, and then draw the complete network. This is Is. Then we have a feedback current going downwards. The term containing feedback is represented as a dependent source. It depends on the output current. We can also show the source resistance Rs. Then I will show the input resistance of the current amplifier Ri and the current in this resistance Ii. Then I will have a dependent current source in parallel with a resistance, and then we will have a load resistance RL containing the current I0. Again we have to find three factors: gain, input resistance and the output resistance. So first of all, let me write down I0. I0 you can write down using current division, Ai into Ii multiplied by R0 by R0 plus RL. But we need to replace this Ii in terms of Is. There are two current sources connected anti-parallel. So what is the net current? It is Is minus beta I0. But I need current in Ri. Ri is in parallel with Rs. So what we will do? We will apply current division. So I will say Rs over Rs plus Ri. What I will do now is replace this Ii in the expression of I0. So I0 is Ai Is minus beta I0 Rs over Rs plus Ri into R0 over R0 plus RL. So Ai multiplied by these two factors will give me the overall current gain AIS. Okay. Now we will collect the term containing I0 on the left hand side. So if you find out I0 by Is as described many times for negative feedback, it is open loop gain by 1 plus open loop gain into feedback factor beta. Okay, that should be the case actually. In negative feedback, the gain reduces by an amount of 1 plus A into beta. Now the next term that we have to find out is the input resistance. For finding input resistance, what I will do is, I will describe the voltage across Ri as Vi and the voltage across RL as V0. So if you apply KCL at the input side, what you will say? What is the incoming current? Is. What are the outgoing current? Beta I0, Vi over Rs plus Vi over Ri. Okay. Now this I0 can be written as beta AIL over 1 plus AIL into beta Is. Why I am taking AIL? Tell me again. Because while finding input resistance, we do not consider the source resistance Rs. So what is this AIL actually? It is AI. Ignore this term because we are not considering source resistance. So only this factor. Okay. Now take the term containing Is on the left hand side. If you take the LCM 1 plus AIL beta, you will see it will become Vi over Rs plus Vi over Ri. Take this term 1 plus AIL beta on the right hand side. It will be Rs over 1 plus AIL beta, Ri over 1 plus AIL beta. That means input resistance with feedback becomes Ri divided by 1 plus AIL into beta. So the input resistance reduces. Why it is reduced? Due to this shunt connection. At the input side we have the shunt connection, so input resistance reduces. The last term that I have to find out is the output resistance. What you can predict? Due to series connection it must increase. So what I will do is, I will apply KCL at this node. What is the incoming current? AI into II. There are two outgoing currents. So what I will say, AI into II equal to two outgoing current V0 by R0 and I0. Now how you can write II? The net current in the input side is Is minus beta I0. Then you will apply current division. Current division is Rs over Rs plus Ri. Now AI multiplied by this current division factor I will call as AIS. Is minus beta I0. V0 by R0 plus I0. Collect I0 term on the right hand side. It is I0 1 plus AIS beta. Now divide it by 1 plus AIS beta into Is. V0 over R0 into 1 plus AIS beta plus I0. So what is the output resistance with feedback? R0 into 1 plus AIS into beta. Okay, as I have told you, the output resistance will increase due to series connection on the output side. Okay, so if you remember just the type of feedback, you can always tell whether the input resistance will be high or low, or whether the output resistance will be high or low. Now the question remains how to judge the type of feedback. Okay, so there can be 2-3 type of questions that can be asked from this topic. The circuit can be based on BJT amplifier, MOS amplifier, or op amp. Okay, So what you have to do is you have to replace even op amp by its internal circuit. What I mean to say by internal circuit means the circuit containing input resistance Ri and a dependent voltage source A into Vi, like this. This is the internal circuit of op amp. Then you have to check one thing, either II depends on feedback or Vi depends on feedback. How you will check? See, if II is equal to source current, that means II does not depend on feedback, so Vi will depend on feedback. So you will call it as voltage mixing or series mixing. Okay. Or if Vi is equal to Vs, then Vi does not depend on feedback. That means II will depend on feedback. So it will be current mixing or shunt mixing. So simply by looking at the circuit from the input side, you can tell whether there is current mixing or whether there is voltage mixing, or you can say series mixing or shunt mixing. Okay, you can tell about that. Is it fine? Once you know the type of mixing, if it is series mixing means we have voltage Vf. Okay. In that case, what you have to do, make II equal to 0. Okay, if it is voltage mixing, then make current 0. In voltage mixing, make current 0 and find Vf. So if Vf is proportional to V0, it is voltage sampling. If Vf is proportional to I0, it is current sampling. So first, by looking at the input voltage and current, I will tell about the mixing, and then I will derive the sampling. If it is shunt mixing means you are mixing the current. If you are mixing current, we have If. If you are mixing current, make voltage equal to 0. Once you make voltage equal to 0, find If. If If is proportional to V0, again voltage sampling. If If is proportional to I0, then it will be current sampling. Okay. So that way you can judge the type of sampling, and by looking at this proportionality constant will be your beta. So you can also tell about the feedback factor beta by finding the proportionality constant. So that way you can judge all the type of feedback in any circuit that you have been given. You will never face block diagrams, you will always face a practical amplifier. So if I summarize, we have seen 4 types of feedback: series, shunt, series shunt, shunt series. If I talk about input and output resistance in series, both are series, so both will be high. Shunt, both are shunt, so both will be low. Series shunt, high, low. Shunt series, low, high. And remember one thing, while finding RIF, ignore RS. While finding R0F, ignore RL. Okay. And based on high or low, you just have to multiply it by a factor of 1 plus A beta or divide it by a factor of 1 plus A beta. As simple as that. You don't have to memorize any derivation or you don't have to derive any result in the exam. Just remember this simple trick. If resistance is increasing, multiply it by that factor. If it is reducing, divide it by the same factor. Okay. So this will be all from this video. In the next one, I'll tell you about what kind of question can be framed based on feedback amplifier. Thank you. Hi guys, in this video I'll be discussing with you all the problems that are based on feedback amplifier so that we can understand what kind of questions can be framed and how to tackle each type of problem. So let us see the first question. An amplifier with open loop gain AV, this is actually a misprinting, it is AV equal to 1000 plus minus 100 is available. It is necessary to have an amplifier whose voltage gain does not vary by more than 0.1%. We need to find the beta for the feedback network. So this variation is given in percentage, whereas originally it is given in absolute value. So if you find out percentage change in AV, it will be 100 over 1000 into 100, that is 10%. So it is saying that initially open loop gain has a variation of 10%, but we need to design a closed loop amplifier whose gain does not vary by more than 0.1%. So we want to reduce the variation in the gain of the amplifier. I told you about the concept of sensitivity, which we derived as 1 over 1 plus A beta. It was del AVF by AVF by del AV by AV. Now this fractional change in closed loop gain is 0.1% or 0.1 by 100. Okay. If you want to come into fraction from percentage, you have to divide by 100. But what is the fractional change in open loop gain? Fractional change in open loop gain is 10% or 10 by 100. That means 0.01 is 1 over 1 plus A beta, or 1 plus A beta is 100. Okay. Or you can say A beta is 99. So how you will find beta? 99. What is the open loop gain? 1000. So 0.099. That is your first part, beta for the feedback network. So whenever you see it is talking about change in the value of gain or percentage change, variation, all these kind of things, you always have to talk in terms of sensitivity. Now it is asking next the gain with the feedback network. We know that gain with the feedback network is AV over 1 plus AV beta. We have seen 1 plus AV beta is 100. AV is 1000. 1 plus AV beta is 100. So gain with feedback is equal to 10. Okay. So it is based on what we learnt in the first lecture of feedback amplifier. Next problem. An amplifier without feedback. Without feedback means open loop. An amplifier without feedback gives a fundamental output of 36 volt with 7% second harmonic distortion. That means now it is talking about distortion in the output when input is 0.028. Okay. Now we are feeding 1.2% of output into input. in a negative voltage series feedback circuit. We need to find the output voltage. If you are feeding the output back to the input, that means we are making it a feedback amplifier. Earlier it was open loop, but now we are making it a feedback amplifier. But first what I need is the open loop gain. So the fundamental output is 36 volt, but the input is 0.028 volt. So if you divide both the things, what you will get is the open loop gain, which will come out to be 1286. Okay, that is the open loop gain of this amplifier. Now it is feeding 1.2% of the output back to the input. So what is beta? Beta is always a fraction, so convert percentage to fraction. It is 0.012. So beta is 0.012. Now I will try and find the closed loop gain. Closed loop gain is open loop gain by 1 plus open loop gain into beta. 1286 by 1 plus 1286 into 0.012. If you substitute this value into the calculator, you will get the value of gain. But it is not asking the gain. What it is asking? Output voltage. So gain is nothing but output upon input. So if you want to find output voltage, you will multiply the gain, this gain, by input. Input is 0.028. Okay. So it will come out to be how much? 2.19 volt. Okay. Directly substitute this value into this AVF. Let us see the next part. It is saying fundamental output is fixed at 36 volt, but second harmonic distortion is reduced to 1%. What is the input voltage? One thing that I told you, while using negative feedback, the distortion is reduced, the gain is reduced, and the bandwidth is increased. So it is saying the distortion with feedback is 1%, but earlier the distortion was 7%. So how distortion is reduced? It is reduced by a factor of 1 plus AV beta. So this was 7% over 1 plus AV beta, means AV into beta is 6. Now what it is saying is we need to find the input voltage for output voltage equal to 36 volt. Now what is the gain of the amplifier? The closed loop gain is always open loop gain over 1 plus AV beta. 1 plus AV beta is 7. So what is this gain of the amplifier? This gain of the amplifier will become how much? Or let me write it like this only, 1286 by 7. This is also equal to V0 by Vs, or you can say 36 by Vs, because it is saying output is 36 volt. Now Vs is equal to basically 36 into 7 by 1286. So it will come out to be how much? It will come out to be 0.196. Okay. That will be the value of supply voltage to obtain fundamental output at 36 volt. Okay. So by the use of change in distortion, I have found out the 1 plus A beta factor, and then I have found the new closed loop gain. Moving to the next problem. An amplifier with open loop voltage gain of 1000 delivers 10 watt of output power at 10% second harmonic distortion when input is 10 millivolt. If 40 dB negative voltage series feedback is applied and output power should remain at 10 watt, determine required input signal and percentage harmonic distortion. Okay. So it has given us that the open loop gain is 1000, but feedback in dB is actually 40. This I told you is 20 log take magnitude because it is positive, 20 log magnitude of closed loop gain by open loop gain. So it will come out to be 20 log 1 plus A beta. Okay. Actually it will be 1 upon 1 plus A beta, but to make it positive I am taking 1 plus A beta. So 2 equal to log 1 plus A beta, or you can say it is log on the base of 10. 1 plus A beta is 10 to the power 2, or you can say 100. Now open loop gain I know 1000. From here I can tell about beta. 99 by 1000 0.099. That is your beta. Now it is saying output power should remain 10 watt. If output power is constant, the output voltage will also be constant. Okay. So how much output voltage we need? Earlier output voltage was gain multiplied by input. Gain multiplied by input. So it is 10 volt. We need it to be constant because output power must be constant. But the new gain is how much? A upon 1 plus A beta, that is 10. 1 plus A beta is 100. That means V0 by Vs is 10, or you can say Vs is V0 by 10, 1 volt. So what is the required input signal? 1 volt. But due to negative feedback, the distortion will also be reduced. Earlier the distortion is 10%, but now it will be 10 by 1 plus A beta. 1 plus A beta is 100. 0.1%. Okay. So by the use of negative feedback, we have reduced the distortion, but the gain has also reduced. So if the gain reduces, for same output voltage, we need more amount of input voltage. Next problem. The following circuit is an example of. We need to judge the nature of feedback. What did I tell you? Replace op amp by its internal circuit. This is the internal circuit of op amp. What is this Vi? Vi is the voltage across Ri. Now see this connection. R2 is connected between negative terminal and V0. This is R2. And R1 is connected between negative terminal and ground. This is R1. This voltage is your Vs, this current is Is, and the current in Ri is Ii. Now see the input side. You can directly say that input current is same as source current. So no feedback in terms of current. If there is no feedback in terms of current, what it will be? It will be voltage mixing, or you can say series mixing. That way I can directly judge the nature of mixing. Now what I need to find is the nature of sampling. If it is voltage mixing, what I will say? Make input current equal to 0. For voltage mixing, make current 0. For current mixing, make voltage 0. If this input current is 0, then the current from here will be the same current going here. They will be in series. If they are in series, what is the voltage here? V. This V can be written as V0 into R1 by R1 plus R2. And what about Vi? How you will write Vi? Vi is Vs minus V. So this V is the feedback voltage which is being subtracted from source, and this feedback voltage is proportional to V naught. So what you can say? Voltage sampling or shunt sampling. So what kind of feedback it is? Series mixing, shunt sampling. So series shunt feedback. Okay. And you also know the value of beta. This is your feedback factor beta. I told you if you derive the feedback quantity, the proportionality constant will directly give you the value of beta. Okay. So that is how you judge the nature of feedback. Next, what is the effect of series feedback in input and output impedance? Directly, both connection are series. In series, the resistance increases. So we will say input resistance with feedback is greater than open loop input resistance. Output resistance with feedback is greater than open loop output resistance. So in one line you can say both input and output resistances increase. Okay. So that is the effect of series feedback. Next, the following circuit is an example of. Again, how you will start? We will draw the internal circuit of op amp. This is Vs R1. In internal circuit, we will have a resistance Ri. But remember, the voltage across Ri should be from positive to negative. So, like this. So, it will be Vi. Then this positive terminal is grounded. Okay. Then this voltage is AV Vi in series with the output resistance R0. We get V0. Now V0 is connected to negative terminal like this. Okay. Now see, this current is Is, this is II. Now see one thing, can you say Is is equal to II? No, because there is one more branch connected here. Okay, there is one more branch connected here. Is is not equal to II. So directly I can say it is talking about current mixing, because if it was not current mixing, the source and the input current would be equal, but both are not equal. Otherwise you can do one more thing. This voltage is Vs. If you apply KVL, what you can tell about Vi? Vs minus Is R1 plus Vi equal to 0. So Vi is minus Vs plus Is R1. Now in this term there is no feedback, so it cannot be voltage mixing. It is actually current mixing. Is it fine? Or you can say shunt mixing. Now if it is current mixing, what you have to do? Make voltage equal to 0. If it is mixing the current, make voltage equal to 0. If you make Vi equal to 0, this terminal will be grounded. So how you will write this I? I can be written as 0 minus V0 by R2. That is minus V0 by R2. So I is proportional to V0. So you can say voltage sampling or shunt sampling. So what kind of feedback it is? It is shunt feedback. Okay. So what I have done? based on the input loop, I have decided whether it is applying KCL or KVL to determine the nature of mixing, and then I have figured out which quantity is to be made 0 and found out the feedback factor. So what is beta here? Beta is actually 1 by R2. Next problem. An amplifier has an open loop gain of 10 to the power 4, input resistance 50 kilo ohm. Find the input resistance of series shunt feedback with a feedback factor of 0.1. The input side we have series connection. Due to series, input resistance will increase. If input resistance increases, you will write RIF is RI 1 plus A beta. 50 kilo ohm 1 plus 10 to the power 4 into 0.1, that is 1000. So it is approximately 50 mega ohm. Okay, as simple as that. For series, the resistance will increase. For shunt, the resistance will decrease. Next problem. A low pass filter with cutoff frequency 30 Hz is cascaded with high pass filter having a cutoff frequency 20 Hz. Find the resulting filter. We are cascading it. If we are cascading it, it means first the response will be like this. We are cascading low pass filter with a high pass filter. Now it will be passed through the high pass filter. What high pass filter is saying? It will pass the frequencies above 20 Hz. But what frequencies do we have? We only have frequencies below 30. It is saying it will pass above 20. It is saying below 30. So the intersection will be from 20 to 30. So what kind of filter it is? Band pass. Simply just think that high pass filter is passing above 20, low pass filter is passing below 30. So their intersection will be from 20 to 30. So that way it will be a band pass filter. Next question. An amplifier has open loop gain 100. Lower and upper cutoff frequency are 100 Hz and 100 kilohertz. A feedback network with a feedback factor of 0.99 is connected to amplifier. Find lower and upper cutoff frequency. Okay. See, due to negative feedback, what do we know? Due to negative feedback, gain reduces, distortion reduces, and bandwidth increases. If bandwidth increases, the lower cutoff frequency should reduce. What I mean to say, I showed you in frequency response as well that earlier the gain or frequency response is like this, but now it is like this. The gain is less, but lower cutoff frequency is lesser than before, and upper cutoff frequency is more than before. So that is what I am saying. Lower cutoff frequency should reduce. So how much will it be? 100 by 1 plus 100 into 0.99. So it will be 1 Hertz. But upper cutoff frequency must increase to increase the bandwidth. So it is 100 kilohertz. 1 plus 100 into 0.99. That is 100 into 100, or you can say 10 megahertz. So remember, the lower cutoff frequency will reduce and the upper cutoff frequency will increase, due to which overall bandwidth of the amplifier will increase. Next problem. Again we have to find the nature of feedback. Okay. So if you observe this circuit carefully, it is an example of collector to base bias in BJT. Now in BJT, the input voltage is the base to ammeter voltage and the input current is base current. See, this is the source current. Can I say IS is equal to II? See this? No. Because this resistance RB is also carrying a current I. So we can't say like this. So what I'll say? It is an example of current mixing or shunt mixing. So as simple as that, if the source current is equal to input current of the amplifier, then it is voltage mixing. If both are not equal, then it is current mixing. Just observe this small thing. Okay. Now, if it is current mixing, what I have to do? What I have to make 0? Voltage. Make VI 0. If I make VI 0, this terminal will be grounded. Then what will be I? I will be 0 minus V0. The voltage of this terminal is V0. 0 minus V0 by RB or minus V0 by RB. So this I is proportional to V0. So it is voltage sampling or shunt sampling. So what kind of feedback it is? It is shunt feedback. Okay. So just observe the current coming out of the source. Is it the input current of the amplifier? Next problem. An amplifier having open loop gain of 100, input resistance 1 kilo ohm, output resistance 100 ohm. A feedback network of feedback factor is 0.99 is connected to the amplifier in voltage series. Find input and output impedance. So first let us observe this voltage series. In this naming, the first term represents sampling and this one is mixing. If you are sampling the voltage or if you are observing the voltage, you have to observe in shunt. So that means at the output side we have the shunt and at the input side we have series. Due to series, the input resistance must increase. Okay. That means 1 kilo ohm 1 plus 100 into 0.99. It will become 100 kilo ohm. But due to shunt output, the output resistance will reduce. R0 over 1 plus A beta. So 100 over 1 plus 100 into 0.99, that is 1 ohm. So just judging the nature of the feedback, you can tell which resistance will increase and which resistance will decrease. Next, the feedback topology in the amplifier circuit shown. Okay. Again, the input voltage is nothing but the base emitter voltage and the input current is the base current. Now this is IS. Now I will ask you the same question. Can I say IS equal to II? Is IS equal to II? You will say yes. IS is equal to II. That I can see directly. That means no current mixing. If there is no current mixing, what mixing will be there? Voltage mixing or series mixing. Now once I know voltage mixing is there, what I'll say? Which quantity will I make 0? Make input current equal to 0. Now see, this input current is actually the base current. If base current is 0, IC is actually equal to IE. But when we talk about amplifier, what we do actually? We remove the DC supply. So in this amplifier, let me remove the DC supply. Even if you want, you can make the model also. So I am making RPi model. These models we have seen multiple times. Okay. This terminal will be grounded, so RC will be connected between collector and ground. Now this is V0. So if I ask you, what if you make IB equal to 0, then this current will be beta IB. What is the current in the output resistance RC? The current in the output resistance RC is actually beta IB. So you can say I0 is minus beta IB, and it is same as, because I0 should be like this, it is same as minus IE. Now if I ask you this VI, so you will apply KVL. What you will say? VS minus IBRS minus VI minus VE equal to 0. VE is this voltage. Okay. But IB has been made 0. So what is VI? VS minus VE. How you will write VE? VS minus IE into RE. But this IE is proportional to I0. That means the feedback voltage is proportional to I0. See, IE and I0 both are equal. So that means in voltage mixing, this feedback voltage is directly proportional to I0. If it is directly proportional to I0, it is current sampling or series sampling. So series mixing and series sampling, it is an example of series feedback. Is this point clear to you? First of all, I have identified what kind of mixing is there, and due to voltage mixing I have derived the feedback voltage, and it is directly dependent upon I0. That is why it is current sampling or series sampling. Next question. A cascade connection of two voltage amplifier is shown in the figure. Actually figure is mixing. So let me draw the figure. This is A1. This is A2. The input and the output resistances are also given. We have to find the overall voltage gain. Now whenever input and output resistances are given, this is an example of multi-stage amplifier. Whenever input and output resistances are given, in that case there is loading effect. Due to loading effect, we cannot directly multiply the gain of the amplifiers. I will write A1 is AV1 into voltage division. What voltage division? Ri2 by Ri2 plus R0 1. That is 10 into 5 by 5 plus 1. That is 50 by 6. What about A2? For A2, you need to know the load resistance. Okay. The load resistance is not given here, but that should have been given. It is 1 kilo ohm. Okay. It is 1 kilo ohm and it is 200 ohm actually. 200 ohm. Okay. So A2 is again by voltage division. AV2 RL by RL plus R02. This concept I have already taught you in multi-stage amplifiers. In multi-stage amplifier, whenever input and output resistances are non-zero, then you have to use the voltage division. 1 by 1 plus 200 ohm is 0.2 kilo ohm. So 5 by 1.2. Now you can multiply the gain after considering the loading effect. 50 by 6 into 5 by 1.2. So it will come out to be 34.7. So those who haven't studied multi-stage amplifier, in that case this question is out of course. But if you have studied multi-stage amplifier for ESE or gate ECE, then you know what formula I am using. This I taught in the multi-stage amplifier in BJT. Moving to the last question. In the AC equivalent circuit shown in the figure, IN is the input current and RF is very large. Find the nature of the feedback. Okay. Now see. In MOSFET, gate current is 0. So the input current is the source current. Now can you say that IN is equal to II? No. That means there is current mixing. Okay. So there is current mixing, there is current I going in RF. Now you can say II is IN minus IF. If it is current mixing, what I will make 0? Make input voltage as 0. Making input voltage 0 means grounding this terminal. This is the input voltage, I am making it as 0. So I am grounding the terminal. Then what is this current I? This is not IF, simply I is 0 minus V out by RF. That is minus V out by RF. So I is proportional to V out. You can say it is voltage sampling, or you can say shunt sampling, and due to current mixing it is shunt mixing. So what feedback? It is shunt feedback. Okay. So that is how you determine the nature of the feedback. If you remember the steps that I have applied, it is very simple to judge the nature of feedback. I hope now you know there can be two type of problem. One based on the first lecture that we studied about feedback amplifier, and second about judging the nature of feedback. This is all from this video. From the next one we will start the oscillators. Hi guys, in the last few videos I have talked to you about feedback amplifiers and how to tackle the different types of feedback and what kind of amplifier is realized using each feedback. But now we will be focusing our discussion to an entirely different topic, that is called as oscillators. Oscillators are entirely separate from amplifier. They don't lie in the category of amplifier, so neither you can classify them in feedback amplifier or any other amplifier for that matter. But they are a very important element in circuit analysis, in circuit designing, in analog designing. Oscillators are very important. Okay, and from even gate or ESE point of view, oscillators play a very important role. So first let us start our discussion from something that you might have used in your laboratory, that is called as the function generator. Now you might have already seen function generator sitting in your laboratory. So my first question to you is, what is this function generator? Now those of you who have used it will say that we use function generator to apply different kind of waveforms. Absolutely right. Function generator is a device that can generate different waveforms. Now what kind of waveforms? Like square wave, like triangular wave, like sawtooth wave, like sinusoidal wave. All these kind of waves can be generated using a function generator. Okay, but does it do any other thing than generating the waveform? Yes. You can also control the frequency, and amplitude of waveform. That also can be done using the function generator. So why is this important? If you have done the lab in which you will be using CRO, for that you always need an input signal, and that input signal is always taken using a function generator. Think like this. Suppose I have designed a circuit. Now I want to simulate that circuit. I want to see the response of that circuit, and to observe the response you need to apply the input. That input waveform itself is being generated by function generator. So what does function generator do? It generates a waveform that can be used to excite the circuit in order to represent or in order to observe the response of the circuit, and that is the functionality of the function generator. Okay. Now for function generator, oscillator is the most important part. Okay, so oscillator is the most important part when we are designing a function generator, and that is why we are moving our study towards oscillator. Now what is an oscillator? An oscillator is a device that can produce an oscillating waveform, or that can produce a waveform which fluctuates between two values. Okay, that is, if I produce a waveform that oscillates between 5 volt and 10 volt, then that device will be called as an oscillator. Oscillator comes from oscillation. Oscillation means motion between two or more than two states. Okay, now if your oscillator generates sinusoidal waveform, if the oscillator is generating sinusoidal waveform, then it is said to be harmonic oscillator. If it generates square wave, triangle wave, or sawtooth wave, that is other waveforms, then it is said to be relaxation oscillator. So sinusoidal oscillators are called as harmonic oscillator, and non-sinusoidal oscillators are called as relaxation oscillator. Now the major difference between amplifier and oscillator is that with oscillator we make use of positive feedback. Okay, always we will make use of positive feedback when we are using oscillator. See this block diagram. The sign or the symbol with the feedback signal is positive. That means it is being added into the supply, or you can say the input signal Xi is sum of supply signal and the feedback signal. So that is why it is called as the positive feedback, because the feedback signal is getting added to the input signal. Okay. Now oscillators are very important. Why oscillators are important? Because they are used in communication equipment. Those who are from ECE background will know that without oscillator we cannot design the receiver as well as the modulators. Okay, so in modulation they will be used for generating carrier wave, for amplitude modulation, frequency modulation. Okay, and they can also be used in transmitter and receiver. Then oscillators can be used in clocks, because in digital we need a clock signal that is a square wave, and that wave is generated using a oscillator. Okay, and also oscillators are sometimes used in triggering SCR, that is for electrical guys. In power electronics we make use of UJT oscillator in order to trigger the thyristor or SCR. Now let us understand how does an oscillator work. See, first of all, let me come in terms of voltage instead of this X. So I am saying the forward path gain is A, similar to feedback amplifier. The forward path gain is A and the feedback gain is beta. This I will call as VI or Vs, Vi, V0. Now you can say that this feedback voltage is beta V0. Now suppose initially, I am explaining the working. Initially V0 is 0. That means Vf is 0. If Vf is 0, this Vi is actually Vs plus Vf. It will be equal to Vs and V0 will become AVi or AVs. So initially V0 was 0, but due to supply voltage V0 is becoming AVs. Now this voltage will generate the feedback voltage, which is beta V0, or you can say A beta Vs. Okay. Now if somehow you manage to make A beta equal to 1, then Vf is equal to Vs. So we don't need Vs, because now the feedback voltage itself will work as the supply voltage. You don't need any supply voltage, or you can say the supply can be removed. So we can say this oscillations will be now self-sustained. Self-sustained means without the need of any external source or any external supply. The oscillations can go on by itself. You don't need to connect any external equipment. Okay. So oscillations will be self-sustained if you make A beta equal to 1. This A beta is called as the loop gain. Similarly, in control system you call GH as the loop gain, but here we are not using G and H, but we are using A and the beta. Okay. And this criteria is called as the Bark-Hussein criteria. So let us discuss upon Bark-Hussein criteria. So what we say, Bark-Hussein criteria says that A beta is equal to 1 for sustained oscillations. Okay. So that means the loop gain, the gain when traversing the closed loop should be equal to 1, or you can say it should be 1 angle 0. That is, magnitude of A beta must be equal to 1, whereas the angle of A beta should be 0, 2 pi, 4 pi, 6 pi, etc. Okay. The angle should be a multiple of 2 pi, or you can say the angle must be 0. So that is called as your Bark-Hussein criteria. It is a criteria which tells us under what condition the oscillation can be sustained. Now suppose if I take A beta less than 1. Just now I showed you feedback voltage was A beta Vs. It means that feedback voltage will be less than the supply voltage. If feedback voltage is less than supply voltage, V0, which is A Vi, will decrease. V0 decreasing means feedback decreases further, and if feedback decreases further, V0 decreases further. So V0 will continue to decrease. So how will V naught look like? If A beta is less than 1, the input voltage is reducing, due to which output reduces, due to which feedback reduces, and V naught reduces further. So it will be like this. Okay. So oscillations will die out. They will not be sustained. Now case 2. Suppose A beta is kept greater than 1. Then Vf equal to A beta Vs means if A beta is greater than 1, it is greater than Vs. V naught, which is A Vi, will increase. If V naught increases, Vf is beta V naught. It will further increase, which will again increase V naught. That means in this case, the oscillation will go on increasing and V naught will go on increasing rather than being sustained. So for sustained oscillation having a constant amplitude, you need A beta to be equal to 1, otherwise oscillations will grow. Either oscillation will die out or oscillation will grow. That is why we keep the value of A beta as close to unity as possible, even if it is not exactly unity. If you can't keep it exactly unity, then keep it as close to unity as possible. Okay. So remember, Bark-Hussein criteria says that product of A and beta should be 1. What is A? A is the gain of the amplifier in the forward path. Beta is the feedback factor. So I am saying A is the gain of amplifier in forward path, and beta is the feedback factor. Okay. Product of them should always be 1. But suppose if I am using an inverting amplifier in forward path, if I am using an inverting amplifier, that means it is providing how much phase shift? 180 degree phase shift. But the net phase shift should be 0 degree or 360 degree. That means for Bark-Hussein criteria, angle of beta must also be 180 degree, such that angle of A beta is integral multiple of 2 pi. Is it fine? So even if you have an inverting amplifier whose gain is negative or it has a phase shift of 180 degree, then feedback must be designed in such a manner that feedback is also providing a phase shift of 180 degree, so that overall phase shift is 0 degree or 360 degree. Now suppose I take an amplifier, suppose I take an oscillator. This is the forward path. This is our beta. Vf, suppose Vi, V naught. Now this Vf is actually beta V naught, or you can say beta is Vf by V naught. Since the voltages are AC voltages, they will have magnitude as well as angle. So I'll say beta is a complex number in which it has real part as well as imaginary part. But A is always real. Gain of the amplifier is always a real value. Okay. We are operating in the midband range. In midband range, gain is always real. Gain is not a function of frequency. Okay. So now when you talk about the Bark-Hussein criteria that A beta is equal to 1, then that means A into beta real plus J A into beta imaginary should be 1. This is real quantity. That means if you compare both the sides, the imaginary part of the left hand side must be 0. Or you can say beta imaginary must be 0. And beta real must be 1 upon A. So that is how we apply the Bar-Hussein criteria when we will be seeing different type of oscillators. You just have to remember, you have to make imaginary part of beta equal to 0 and real part of beta equal to 1 upon A. Then your Bar-Hussein criteria can be satisfied. So what does Bar-Hussein criteria says? If you make the loop gain equal to unity, then the feedback signal can itself work as the input signal. You no longer need the input signal and oscillations will be self-sustained. Okay. So that means the feedback signal can also work as the input signal. Okay. Then input signal is no longer required in a oscillator. Now the question that comes to mind is, what is the difference between amplifier and oscillator? Now when you talk about amplifier, what does it do? It increases the amplitude and power of AC input signal, right? Now where does this power come from? This power is derived from DC biasing. Okay, the DC sources that we have connected, they will supply this power. What does an oscillator do? It generates an oscillating waveform without any external source. Okay, without the help of any external source, it can generate an oscillating waveform, and the frequency and other parameters of waveform, most importantly frequency, are controlled by passive components such as resistance, inductance, capacitance connected in the oscillator circuit. Okay, so we will control the waveform parameter, mainly frequency, using the passive components that we have connected in the oscillator. Is it fine? Now what are the different type of oscillators that we will be studying in this topic? See, the oscillators are mainly classified into two categories. One is called as the audio frequency oscillator. Audio frequency means the frequency of waveform generated will lie in the audible range. The other is called as radio frequency oscillator. Radio frequency means high frequency. So audio frequency means between 20 Hz and 20 kilohertz. Radio frequency means greater than 20 kilohertz. So what are the oscillators that will come under audio frequency oscillator? We will first see VN bridge oscillator. Then we will see RC phase shift oscillator. They both are audio frequency oscillator. What about radio frequency? Here we will see LC oscillator, in which we will see three type of oscillator: Hartley, Colpit and Clap oscillator. and also the second is crystal oscillator. Crystal oscillator you might have heard about if you have studied microprocessor. Crystal oscillator is used with microprocessor in order to supply the clock signal. Okay, they have high frequency, so it is called as radio frequency oscillator. Okay, so RC oscillator will design a sinusoidal wave, that is, it will be a harmonic oscillator. Okay, LC oscillator will give us the square wave, whereas crystal oscillator will give the sawtooth wave. So RC oscillator sinusoidal, LC oscillator square, crystal oscillator triangular or sawtooth type of wave. So these all oscillators we will cover in the next few lectures in order to understand how does an oscillator work and how it will be used in our system. So in this one I'll be teaching you one oscillator, that is the VN bridge oscillator. Now if you see the structure of this VN bridge oscillator, you will see the passive components include resistance and the capacitance. So it is also a type of RC oscillator. So you can say there are two type of RC oscillator, VN bridge oscillator and the RC phase shift oscillator. Okay, so when we are designing for low frequency we are using R and C. When we are designing for high frequency we will be using L and C. Okay, so now one thing that we will do here is understand what is the frequency of oscillation of this VN bridge oscillator and how we will analyze this circuit. Now see this. This branch is connecting output to the positive terminal of op amp. That is why I will call it as positive feedback. And since it is an oscillator, you can see we don't have any input signal because oscillator oscillations are self-sustained. It does not need any input signal. So what is the principle of op amp? In op amp we don't have any input current or current at the input terminals. This both currents will be 0 ampere. That means R1 and R2 are in series and this branch ZF and Z1 is also in series. So if I ask you the voltage of positive terminal, what you can do? Apply voltage division V0 into Z1 by Z1 plus ZF. What about negative terminal voltage? It is V0 into R2 by R1 plus R2. Now what is the input voltage of the op amp? The input voltage is actually the difference of the positive and the negative voltage. So it is V0 Z1 divided by Z1 plus ZF minus R2 divided by R1 plus R2. Now see, this input voltage is directly proportional to output, so this will be called as your feedback voltage. In oscillator we don't have any input voltage, but the feedback voltage itself works as the input voltage. Now let me write down Z1 and ZF. ZF is R plus 1 by SC. So you can say SC R plus 1 by SC. What about Z1? R dash parallel with 1 by SC dash. That is R dash over 1 plus SC dash R dash. So when you find out this term Z1 by Z1 plus ZF, if I simplify R dash over 1 plus SC dash R dash over SCR plus 1 by SC plus R dash over 1 plus SC dash R dash. Now it will become R dash over into SC divided by SCR dash 1 plus SCR into 1 plus SC dash R dash. Okay. This I have just simplified the term Z1 over Z1 plus ZF. Okay. Now what we can do is, we can further simplify by opening the braces. S square R R dash C C dash plus S C R C dash R dash C R dash plus 1. Okay. Now if you write down beta, what is beta? Beta is the ratio of feedback voltage and output voltage. So it is Z1 over Z1 plus ZF minus it will be R2 over R1 plus R2. That means SCR dash by S square RR dash CC dash plus S CR C dash R dash plus CR dash plus 1 minus R2 by R1 plus R2. Now if you want to come into frequency domain, you will replace S by j omega CR dash. J omega whole square is minus omega square plus j omega RC R dash C dash R dash C. Now I told you, when applying Bar-Hussein criteria, you will replace the imaginary part of beta, or you will equate the imaginary part to 0. In order to find the imaginary part, we will have to rationalize this expression. So I will multiply the conjugate of the denominator in the numerator. So conjugate will be this. Okay. And in the denominator, what I will have? 1 minus omega square RR dash CC dash whole square plus omega square RC R dash C dash R dash C whole square. Now if you take out the imaginary part of beta, this term is real. So imaginary part will come from the first term. J into J, that is the second term, will be real, but the first term will be imaginary, because imaginary into real is imaginary. So we will write omega C R dash 1 minus omega square R R dash C C dash must be 0. It will also have some denominator, this denominator. But since we are equating it to 0, the denominator will not matter. If you are equating it to 0, omega square R R dash CC dash must be 1. Or you can say omega will be 1 by under root R R dash C dash. Or you can say the frequency of oscillation. From here I have derived the frequency of oscillation. F will come out to be 1 by 2 pi under root R R dash C dash. Okay. That will be the value of the frequency produced by this oscillator. Okay. Now once we know this, what will be the remaining value of beta? Second term, if you see, j into j, minus 1, minus will be plus 1, omega square CR dash RC R dash C dash R dash C by 1 minus omega square r dash c dash whole square plus omega square rc plus r dash c dash plus r dash c whole square minus r2 by r1 plus r2. Now see this thing. When we were equating the imaginary part of beta to be 0, okay, when we were equating imaginary part of beta to be 0, we equated this term equal to 0. 1 minus omega square is this. I will write as omega naught f naught. Here also I will write omega naught. Okay. That means we were equating this 1 minus omega square term to be 0. So this term will also be 0. So what beta remains? Omega naught square cr dash rc plus r dash c dash plus r dash c by the first term in denominator goes to 0. So it is omega naught square rc plus r dash c dash plus r dash c whole square minus r2 by r1 plus r2. This term gets cancelled. This will also get cancelled. So what we will get in beta? We will get that beta is actually equal to cr dash by rc plus r dash c dash plus r dash c minus r2 by r1 plus r2. Okay, that will be the value of beta when we have applied the Bark-Hussein criteria for oscillations. Okay, is this much fine? Okay, now let me take one case. If r equal to r dash and c equal to c dash, if r equal to r dash and c equal to c dash, what is this oscillation frequency? This will become r square, this will become c square. It will be 1 by 2 pi rc. What about beta? If rc is equal to r dash c dash, it will be 3 rc. It will be rc. So 1 by 3 minus r2 by r1 plus r2. That will be the value of beta. Okay, and you can find out the relation between r1 and r2 if you know the value of a, because a into beta must be 1. Now how to find the value of a? See this figure. This is the amplifier. Because in negative feedback we have the amplifier, but for positive feedback we have the oscillator. So what I need is the forward path gain A, and then only I can tell about the beta. Now see, the feedback voltage is connected at the positive terminal. So it is acting as the non-inverting amplifier. See, I told you in oscillator the feedback voltage will itself play the role of input. So if you consider feedback voltage as input, the input is connected at which terminal? Positive terminal. So it is a non-inverting amplifier. What is the gain of non-inverting amplifier? The gain of non-inverting amplifier is 1 plus Rf by R1, that is 1 plus R1 by R2, or you can say R2 plus R1 by R2. Now we know that A beta must be equal to 1. So R2 plus R1 by R2 multiplied by beta was 1 by 3 minus R2 by R1 plus R2. This must be 1. So R2 plus R1 by 3 R2, if you multiply it inside, minus 1 is equal to 1. Okay. So how much will it become? R2 plus R1 by 3 R2 should be equal to 2. Okay. Is there some calculation mistake? Let me check once. It will be 1 by 3 minus R2 by R1 plus R2. Okay. And what is the gain of the non-inverting amplifier? The gain of the non-inverting amplifier is 1 plus R2 by R1. 1 minute. We will not go like this. What I'll do is I'll assume an ideal op amp. Okay. We will assume an ideal op amp. What is the gain of ideal op amp? The gain of ideal op amp is infinite. If the gain of ideal op amp is infinite and we know A beta equal to 1, which means beta equal to 1 by A, it will tend to 0. If beta tends to 0, it means 1 by 3 minus R2 by R1 plus R2 must be 0. Or you can say 3R2 is R1 plus R2, or you can say R1 equal to 2R2. It means if you assume R equal to R dash and C equal to C dash, then R1 must be equal to 2R2, then only you can design the VN bridge oscillator. So in VN bridge oscillator, what you need to remember is the frequency of oscillation, which is 1 by 2 pi under root R dash C C dash. Okay. That is the condition that you need to remember. Is it fine? Also, one more thing that we can do here for the general case. For the general case, what was beta? Beta was C R dash by RC, R dash C dash, R dash C minus R2 by R1 plus R2. For the case of ideal op amp, A tends to infinity, due to which beta must tend to 0, so that A beta equal to 1. If beta is 0, you can say C R dash by RC plus R dash C dash plus C R dash should be equal to R2 by R1 plus R2. If you take reciprocal on both the sides, by CR dash, it is equal to R1 plus R2 by R2. So it is 1 plus R by R dash plus C dash by C is equal to 1 plus R1 by R2. So this gets cancelled. So this is the condition from beta Okay. So what you have to remember in VN bridge? This is the first condition that you have to remember. The second is the oscillation frequency 1 by 2 pi under root R, R dash, C, C dash. If R and R dash are equal and C dash are equal, you will get the condition that we derived earlier, R1 equal to 2R2. You will get from the first one if R and R dash are equal and C dash are also equal. So just remember these two conditions from the VN bridge oscillator, and remember it is audio frequency oscillator. It is used to generate small frequencies, low frequencies in the audible range from 20 Hz to 20 kilohertz. Okay. So RC oscillators are always used at low frequencies because their response is stable at low frequency. Okay. So if I summarize what we have covered in this video, first of all I have told you about function generator. Then I told you oscillator is an important part of any function generator, and in oscillator we saw Bark-Hussein criteria, that is for sustained oscillation A beta must be equal to 1. Then we saw that there are two types of oscillator, audio frequency and radio frequency. In audio frequency we have RC oscillator, in which we covered VN bridge oscillator in this video. In VN bridge oscillator we saw only passive components were R and C, and we derive two conditions, that is R by R dash plus C dash upon C is equal to R1 by R2, and the second one is frequency is 1 by 2 pi under root R dash C dash, and the response of VN bridge oscillator is only stable at low frequency. That is why it is audio frequency oscillator. Its response will become unstable at high frequency. That is why we don't use VN bridge oscillator at high frequency. We only use up to 20 kilohertz. Okay, and that is due to op amp. Is it fine? So in the next video we will cover more about the next RC oscillator, that is the RC phase shift oscillator. That we will cover in the next video. Thank you. Hi guys, in the previous video I introduced to you the concept of function generator. So I told you that many of you might have already used function generator in your laboratories, where you were applying different kind of waveforms to the circuit. Then I told you the most important part of a function generator is a oscillator. Okay, and we saw in oscillator we have to satisfy Bark-Hussein criteria, and we have to configure it in positive feedback configuration in order to generate self-sustained oscillation. What was Bark-Hussein criteria? That product of gain and feedback factor must be unity. A beta equal to 1 means A beta equal to 1 angle 0, that is magnitude of the loop gain should be 1 and angle of loop gain must be 0. That was the Bark-Hussein criteria. And then what we did? After that I told you that there are two type of oscillator. One is the audio frequency oscillator. Okay, in which I told you there are two oscillators mainly, VN bridge, which we covered in the previous video, and RC phase shift oscillator, which we will cover in this video. Okay, in VN bridge oscillator we derived, the result was R over R dash plus C dash by C equal to R1 by R2, and the oscillation frequency was 1 by 2 pi under root R dash C dash. Okay, that we covered in the previous video. In this one we will focus on RC phase shift oscillator. Okay, so the RC phase shift oscillator is also a sinusoidal oscillator. That means it will generate a sinusoidal waveform. Okay, but it is used for different applications than VN bridge oscillator. Like it can be used as a local oscillator for synchronous receiver, musical instrument, study purposes. Okay, so it is different from your VN bridge oscillator, but it also generates the sinusoidal oscillation. Now the basic structure of RC phase shift oscillator using op amp is on your screen. You can see it has two parts. One is the feedback amplifier, basic amplifier, and other is the feedback network. Okay, and if you see, this amplifier is configured in inverting configuration. Okay, why I am saying inverting? Because see, the feedback signal which works as the input signal for the oscillator is connected at the inverting terminal. Okay, if the feedback signal was connected at non-inverting terminal, then it would be working as a non-inverting amplifier, but it is connecting at the inverting terminal, so it is working as an inverting amplifier. So it will provide a phase shift of 180 degree. It is configured in inverting configuration. So it will provide a phase shift of 180 degree. But in Bark-Hussein criteria, we told that in loop gain, in the closed loop connection, the phase shift must be 360 degree or 0 degree. So in Bark-Hussein criteria, what is the phase shift required? It should be 360 degree. So 180 degree is being provided by this amplifier. Rest 180 degree will be provided by feedback network. Now this feedback network consists of resistance and capacitance, and that is why it is called as RC phase shift oscillator, because RC network is being used to provide 180 degree phase shift in order to satisfy the Bark-Hussein criteria. So the basic name of this amplifier, of this oscillator, is RC phase shift oscillator. Now as you can see, we have three stages of R and C, three capacitors and three resistors. So three stages have been cascaded in order to provide 180 degree phase shift. Okay. So first of all, what is the gain of amplifier? If I start analyzing this network, what is the gain of amplifier? The gain is minus RF over R1. Okay. That is the gain. But I need now is, I already have the value of A, but we need A beta equal to 1. So we need to find the value of beta. In order to find the value of beta, we will draw the feedback network. This voltage is V0. Then we have a capacitor, then a resistor, then again a capacitor, again a resistor, then again a capacitor, again a resistor. What is the output voltage here? It is Vf and this is V0. So what we know is beta is always Vf over V0. But see one thing, don't think that you will find the transfer function of one RC network and then multiply it 3 times to find Vf by V0. Why? Because we cannot directly multiply the transfer function 3 times because of loading effect. The limitation of cascading is that transfer function cannot be multiplied together until there is loading effect. Okay. So here we have loading effect. Why there is loading effect? Because current will pass from one stage to the other, and whenever there is current flow between the two stages of cascaded configuration, then it is called as the loading effect. Okay. So don't find transfer function of one stage and multiply it 3 times. We have to find it manually. So now the real challenge starts, how to find this beta Vf by V0. So let me show you how I will derive it. Okay. It is calculation intensive process, so pay attention. Let me remove this information and start the derivation. So I will not approach this problem from the left hand side, but rather I will approach from the right hand side. Suppose this is the current I. What is this current I? Vf by R. There is no current here. Okay. There is no current in Vf, so this current I will come from here. This is the current I. Okay. If this is the current I, the same current is going from capacitor to resistor like this, then what is this voltage? Suppose V1. V1 will be Vf plus I into 1 by SC. Okay. So VF plus VF by SCR. That is your V1. Then what is the current here? Suppose I1. I1 is V1 by R. What is the current here? It will be I1 plus I. So if I want to find out V2, V2 will be V1 plus I1 plus I by SC. V1 is how much? VF plus VF by SCR plus I1 by SC means V1 by SCR, because I1 is V1 by R plus I by SC. I by SC is VF by SCR. So VF plus 2 VF by SCR. Now substitute V1 in this equation. V1 is VF by SCR will come, plus VF by SCR is already there, so SCR square. So it is VF plus VF over 3 SCR, sorry, 3 VF by SCR plus VF by SCR square. Okay. Now I have V2. I can find this I2. I2 will be V2 by R. And then you can write V0 as V2 plus I1 plus I2 plus I into 1 by SC. So V0 is V2. V2 is how much? VF plus 3 VF by SCR plus VF by SCR square. This is V2 plus V2 by R is I2. I1 plus I. I1 plus I will be, I1 is V1 by R. I is VF by R into 1 by SC. So VF plus 3 VF by SCR plus VF by SCR square. Now see this term, V2 by R into 1 by SC, it is V2 by SCR. V2 is this one. V2 by SCR is VF by SCR plus 3 VF by SCR whole square plus VF by SCR cube. Second term, V1 by R and 1 by SC, V1 by SCR. V1 by SCR will be VF by SCR plus VF by SCR square. And the last term is VF by SCR. Now collect the corresponding terms. VF, 3 VF by SCR, 4 VF by SCR, 5 VF by SCR, 6 VF by SCR. VF by SCR square, 4 VF by SCR square, 5 VF by SCR square. And the last term is VF by SCR cube. Now take LCM. SCR cube plus 6 SCR square plus 5 SCR plus 1 by SCR whole cube is V0 by VF. But we needed VF by V0. So how much will it come out to be? SCR cube by SCR cube 6 SCR square 5 SCR plus 1. Okay, that is the value of beta. Now I will convert it to j omega. So j omega CR whole cube. Okay, then j omega CR cube plus 6 j omega CR square plus 5 j omega CR plus 1. That is minus omega CR cube. J cube is minus j omega CR cube minus 6 j square is minus 1 omega CR square plus 5 j omega CR plus 1. Now I know in order to apply Bar-Hussein criteria, what I will do is I will bring this minus j downwards. I will divide numerator and denominator by minus j, or you should multiply both numerator and denominator by plus j. Okay. Now we know imaginary part of beta must be 0. Beta must be real. So I will equate the imaginary part of denominator to be 0. What is the imaginary part? 1 minus 6 omega CR square. That means omega will be 1 by RC under root 6. Or you can say the oscillation frequency will be 1 by 2 pi RC under root 6. Is it fine? So what I have done, I have brought all the imaginary terms in the denominator and then reduce the imaginary part of denominator to be 0. Now what beta remains is the real part. That is omega CR cube by omega CR cube minus 5 omega CR. Or you can write like this, 1 by 1 minus 5 by omega CR square. Now what is omega CR square from this equation? It is 1 by 6. So 1 over 1 minus 5 into 1 by 6. Sorry, 5 into 6 it will become. So minus 1 by 29. Okay. So beta will come out to be minus 1 by 29. Now once beta is minus 1 by 29, A was how much? A was minus RF by R1. Now we know what should be the value of A into beta. A into beta must always be equal to 1 as per Bar-Hussein criteria. So we will multiply both these values and then equate them to 1. So minus RF by R1 into minus 1 by 29 equal to 1. It means RF equal to 29 R1. So that should be the relation between RF and R1 in order to operate this circuit as a oscillator. Okay. So the only thing that you have to memorize in this one is the formula for frequency, and also keep in mind how did I derive this, because if sometimes instead of 3 stages it gives you 2 stages, you can derive the transfer function. Okay. Next, suppose if I want to design the same oscillator using BJT. Instead of op amp, I want to use BJT. So what I am essentially doing is, I am replacing the active element. Active element in previous circuit was op amp. Here I am replacing the active element by BJT. See, this is the amplifier. Which amplifier is it? It is common emitter amplifier. We know in common emitter amplifier there is 180 degree phase shift. So this amplifier will provide 180 degree phase shift in V0, and then by using 3 stages of RC network, which is your feedback network, we will generate another 180 degree phase shift in order to make the net phase shift 360 degree or 0 degree. Okay, so it is using a common emitter amplifier. Then you can see it also has a bypass capacitor. So it has bypass capacitor. So RE is used to bias the transistor and improve thermal stability. Okay, here we are using RE just to improve thermal stability and bias the transistor. It will not be used in the AC analysis. Now suppose I want to draw the AC model of this circuit. So for drawing AC model, what you have to do? You have to ground the DC source. If you ground this DC source, R1 and R2 will come in parallel. So R1 will be in parallel with R2. Okay, this is the base terminal. Then between base and emitter, I will show the resistance. Either you can show HIE or you can show R pi. That is your choice. IB. Then emitter will get grounded due to this CE. And between collector and emitter, what you will show? You will show a current source HFE IB. Then between collector and ground, there will be resistance RC. And collector voltage is V0, which is then connected to a network of resistance and capacitance. Okay, C R C R C. Now see this terminal goes through R3, and due to R3 it is connected to base. Now you will check what is the input resistance, and that resistance will be connected between base and ground. So what I will show here is the input resistance Ri dash. Because the resistance between base and ground, this terminal is actually base terminal, this one. Okay, the resistance between base and ground will be Ri dash. Okay, that resistance I have shown here. Now how to find Ri dash? If you see from the input side, there are 3 resistances, R1, R2 and HIE. It is approximately equal to HIE. So if you see, the resistance of this branch is R3 plus Ri dash. R3 plus Ri dash must be equal to R, so that all stages are identical. Otherwise what will happen? In some stages we will have resistance R, but in other stage we will have a different resistance. So R3 is chosen such that their sum R3 plus Ri dash must come out to be equal to R. Okay, keep this in mind. Now we define a factor K as RC upon R, because if you see, this resistance is RC, but this resistance is R. Now if you solve this, the oscillation frequency will come out to be, I am directly writing the expression, 1 by 2 pi RC under root 4K plus 6. Remember, K is the ratio of RC and R. And the condition for oscillation, just like VN bridge, the condition for oscillation is that HFE must be greater than 4K plus 23 plus 29 by K. If you want the minimum value of HFE, you will differentiate HFE with respect to K and make it equal to 0. So what it will come out to be? 4 minus 29 by K square equal to 0. So K will come out to be 2.7 and HFE will come out to be 44.54. These are the direct condition which you have to remember. They will not be used in GATE but in other exams. Okay. Direct question based on this expression will not be asked in GATE. Similar type of circuit I can generate using FET. FET can be JFET or MOSFET. So instead of BJT, now the active element in our circuit is your FET. The active element is FET instead of BJT or your op-amp. Again see, same kind of circuit we are using. We are using 3 stages of cascaded R and C. And what kind of amplifier we are using? We are using in FET common source amplifier, and we know common source amplifier provides 180 degree phase shift. Okay, it is providing 180 degree phase shift, and that is why this feedback network will provide additional 180 degree phase shift, so that the total phase shift is 360 degree, which satisfies the Bark-Hussein criteria. Okay. So here also, if you analyze this circuit, the oscillation frequency comes out to be 1 by 2 pi RC under root 6, same as the op-amp. Okay, the only difference is in BJT, and here the voltage gain of amplifier beta will come out to be minus 1 by 29. So the voltage gain of amplifier should be minus 29. Okay, then only A beta can be equal to 1. The voltage gain of FET amplifier should be 29. Okay. So if we summarize what we have covered in this video, I have told you about RC, phase shift oscillator. In this we first saw using op-amp, in which we saw the oscillation frequency was 1 by 2 pi RC root 6, beta was minus 1 by 29. Then we saw using BJT, the frequency was 1 by 2 pi RC under root 4K plus 6, where K was minus RC by R. In FET, we get the same results as op-amp. Okay. So direct question in GATE exam can be asked from the first one. Other two cases will not be asked in the GATE exam. So this is all about the audio frequency oscillator. In the next video, we will start with the radio frequency oscillator, that is Hartley, Colpit, such kind of oscillator. Okay, that we'll cover in the next lecture. Thank you. Hi guys, up to now what we have covered is, in the previous two videos I have told you about the RC oscillator. The first RC oscillator that we studied was VN bridge oscillator, and the second one was RC phase shift oscillator. And I told that the RC oscillators are audio frequency oscillator, that is they are used to generate frequencies in the audio frequency range, which is actually low frequency. So now we will shift our attention on the LC oscillator. LC oscillators are radio frequency oscillator, high frequency oscillator. So they are used to generate frequencies almost above 500 megahertz. Now these LC oscillators basically use a tank circuit or a LC circuit. Okay, we know that LC circuit is called as a tank circuit. They use LC circuit in positive feedback configuration in order to generate oscillation. Why we need positive feedback? According to Bark-Hussein criteria, any oscillation can be sustained only if there is positive feedback. But that positive feedback here is applied by means of tank circuit, and that is why they are called as the LC oscillator. Okay, they can be used in signal generator, frequency mixer, tuner, sine wave generator and RF modulator. These are certain application of LC oscillator. Now on your screen you can see that the LC oscillator general circuit is shown. At the top with op-amp we have constructed a inverting amplifier. This one is inverting amplifier. And at the bottom we have connected a feedback circuit by means of three impedances Z1, Z2 and Z3. So there are three impedances which are combinedly forming the feedback circuit, and that is called as a split tank. Now this inverting amplifier is providing a phase shift of 180 degree, but in Bark-Hussein criteria the loop gain should have a phase shift of 0 degree or 360 degree. That is why the split tank should also provide a phase shift of 180 degree, and then only this circuit can work. Okay, for 0 degree phase shift, the split tank as well as the inverting amplifier both must provide a phase shift of 180 degree, so that the net phase shift is 0 degree or 360 degree. Now let us see how does this split tank work. How does this provide a phase shift of 180 degree? So let us take Z1 and Z2 as two resistances. Suppose they are equal resistances, and we have a voltage, suppose V in. Okay, this voltage is suppose V2, V1, this is V2, this is ground. Okay, actually this terminal is not directly grounded, it is connected to this non-inverting terminal. Okay, and then it is grounded. So where it is connected? It is connected to the non-inverting terminal. We know that non-inverting terminal or any input terminal of op-amp does not have any current. The input current to the op-amp is always 0. If input current is 0, the current through both R must be same, because this terminal is connected to non-inverting terminal in which the current will be 0. So the current through both the resistances will be same. Now current from V1 will be V1 minus 0 by R, and current from the second resistance will be 0 minus V2 by R, which means V1 equal to minus V2. Or you can say V1 and V2 have phase shift of 180 degree, and that was my objective. Using the split tank circuit, I want to realize a phase shift of 180 degree. And how is that getting satisfied? Because the current through the middle terminal is 0, because it is connected to non-inverting terminal of the op-amp. Hence the current through both Z1 and Z2 will be identical. Okay, so we can provide a phase shift of 180 degree. Now what kind of circuit can be used in the split tank circuit? One example I have showed you. In this example I took both the resistances. We want a phase shift of 180 degree. Similarly, what you can do? You can use two capacitors Similarly, you can use two inductors. So these three circuits can be used in the split tank circuit to provide 180-degree phase shift. Now coming back to the original circuit. When we come back to the original circuit, we have an inverting amplifier and we have a split tank. So what is the gain of inverting amplifier? The gain of inverting amplifier is actually minus RF by R1. Okay. That is minus RF by R1. That is the gain of inverting amplifier as we derived in the op amp section. Okay. Now, what about the split tank? So let me draw the split tank again. The split tank is somewhat like this. Okay. This is Z1. This is Z2, right? Let me check the previous diagram. Yeah, Z1 and Z2. In middle there is ground. This voltage is V0. This is Vf. Now what I will say? I will say that the current through Z1 and Z2 will be identical. Both will be I. So how you will write the first I? V0 minus 0 by Z2, and the second current 0 minus Vf by Z1. So Vf is equal to minus V0 Z1 by Z2. That is your feedback voltage. So we know that the ratio of feedback voltage and output voltage is called as the feedback factor beta, which is minus Z1 by Z2, and the gain of amplifier is A. Now what about Bark-Hussein criteria? In Bark-Hussein criteria, A beta must be equal to 1. So RF by R1 into Z1 by Z2 must be 1. Okay. If it is 1, then what you can say? We can find the relation between RF and R1. RF equal to R1, Z2 by Z1. But what we need is the relation between, or what you can say, we also need the oscillation frequency. So how you can find the oscillation frequency? For that you have to observe that this current I will flow in the loop. If I current is flowing in the loop, then I can apply KVL. I Z2 plus I Z1 plus I Z3 equal to 0. So what you can say? Z1 plus Z2 plus Z3 equal to 0. So based on Bark-Hussein criteria, we can find the value of the feedback resistance, and by equating the sum of the three impedances to 0, we can find the frequency of oscillation. Okay. So this condition is used to determine the frequency of oscillation of the LC oscillator. Okay. So remember how you find the frequency of oscillation? By equating the sum of the impedances to 0. Okay. And how you find RF? By using Bark-Hussein criteria. Now if the sum of three impedances is 0, all three cannot be inductor or capacitor, because then their sum can never be 0. We know that when we talk about impedances, inductor and capacitor cancel each other. So Z1, Z2, if both are capacitor, then Z3 must be the inductor. If Z1 and Z2 are capacitor, if Z1 and Z2 are inductor, then Z3 must be capacitor. Are you getting my point? Sum of three capacitances or inductances cannot be 0, but inductance and capacitance can cancel each other. That is why if you are using Z1 and Z2 as capacitor, Z3 must be the inductor. If Z1 and Z2 are inductor, Z3 must be the capacitor. So we designed two oscillators. one containing two inductor plus one capacitor, which is called as Hartley oscillator. Then the second one, two capacitor plus one inductor, it is called as Colpitts oscillator. Okay, so we designed two types of oscillator based on this LC oscillator theory. Okay, so let us start with our first oscillator, that is your Hartley oscillator. Now see, the circuit is same that we studied earlier, an inverting amplifier using R1 and RF, but now Z1, Z2, Z3 are not arbitrary, but they have been shown that we are using two inductors and one capacitor. So what about Z1? Z1 can be written as SL1. What about Z2? Z2 can be written as SL2. What about Z3? 1 by SC. Okay. So now we know the value of Z1, Z2, Z3 instead of keeping them as the arbitrary value. Okay. Now what I told is, by equating the sum of three impedances to 0, we can figure out the operating frequency or oscillation frequency. So SL1 plus SL2 plus 1 by SC equal to 0. If you go in frequency domain, S will be replaced by j omega. J omega L1 plus L2 plus 1 by j omega C. So j omega L1 plus L2 equal to minus 1 by j omega C. Now take j omega on the left hand side, is equal to minus 1 by L1 plus L2 into C. Now j square is minus 1. So we can say that omega is 1 by under root C multiplied by L1 plus L2, or the operating frequency is 1 by 2 pi under root C multiplied by L1 plus L2. So that is the operating frequency of your Hartley oscillator. So we write it also as 1 by 2 pi under root C into L equivalent. Now if you have magnetically coupled inductor, if the two inductors are magnetically coupled inductors, then the equivalent inductance is actually L1 plus L2 plus 2M. Okay, so equivalent inductance is L1 plus L2 if both are decoupled, but if both are coupled, then inductance is L1 plus L2 plus 2M. Then what I told is, I also told that RF by R1 should be equal to Z2 by Z1, which means RF is R1 into L2 by L1, because Z2 is SL2 and Z1 is SL1. So from here we can get the relation between RF and R1. Now we can also realize the same oscillator using BJT. So what I have done is, op-amp was which kind of amplifier? We were using inverting amplifier. That is an amplifier which provides 180 degree phase shift. So if you want 180 degree phase shift in BJT, we can make use of common ammeter configuration. Common collector and common base provide 0 degree phase shift, but common ammeter configuration will provide 180 degree phase shift. So see this circuit. This is nothing but a common ammeter amplifier with self bias or voltage divider bias. Common ammeter amplifier with voltage divider biasing. Okay, so that is your amplifier implemented using BJT, and we are using the same type of split tank circuit. Okay, The same thing we can do in MOSFET. For MOSFET, if you need 180-degree phase shift, which kind of amplifier you will use? We will make use of common source amplifier. Okay. Now, what are the points that you need to remember? That it has variable frequency. How variable frequency? If you see, this capacitor is variable, and we know that the operating frequency is 1 by 2 pi under root C into L equivalent. So by varying the value of C, we can vary the value of operating frequency. Okay. The drawback is harmonic content is high. Harmonics, what are harmonics? Harmonics are sinusoidal components which have frequency multiple of the fundamental frequency. What is the fundamental frequency here? It is F0. That means we will not have a single signal, but we will have multiple components, and they will have frequency multiple of F0, and that is why its harmonic content will be very high. Okay, so that means it cannot generate a pure sine wave, it will have harmonics, so the waveform will be distorted. Okay. Second, third, it has low frequency. Why low frequency? Because L equivalent is high. Inductor can never be very small value, so inductor is high, and that is why frequency is low. Secondly, it will also be bulky, because inductors always have large size, so the size of this oscillator will be bulky. Okay, so that is the point, some points that you have to remember about Hartley oscillator. Moving to the next one. The next type of oscillator is Colpit oscillator. Now see what we have done. We have used the same inverting op amp, but now we are using two capacitors and one inductor in the split tank circuit. Earlier there were two inductor and one capacitor. Now we have two capacitor and one inductor. If you write the value of Z1, Z2 and Z3, Z1 is 1 by SC1, Z2 is 1 by SC2, Z3 is SL. Now when we want to find out the frequency of oscillation, then what we will do? We will make Z1 plus Z2 plus Z3 equal to 0. So 1 by SC1 plus 1 by SC2 plus SL equal to 0. If you replace it by j omega, 1 by j omega C1, 1 by j omega C2 plus j omega L equal to 0. So 1 by j omega, 1 by C1 plus 1 by C2 equal to minus j omega L. Now take this j omega on the right hand side. That means omega square L. So what will be omega? 1 by under root L. Now 1 by C1 plus 1 by C2 will be C1 plus C2 by C1 C2. Okay, that will be the case. Sorry, 1 by L. So actually it will be C1 C2 by C1 plus C2. That means you can also write as L into C equivalent, or the frequency will be 1 by 2 pi under root L into C equivalent, where C1 and C2 are in series. So C equivalent is actually C1 C2 by C1 plus C2. Okay, so in the previous Hartley oscillator, what we were getting? C multiplied by L equivalent, but in Colpit oscillator what we are getting? L multiplied by C equivalent. What change I have done? I have used two capacitors and one inductor. Earlier we were using one capacitor and two inductor. Similar to the previous case, we can replace this inverting amplifier by a common emitter BJT amplifier. Okay, we can replace it by a common emitter BJT amplifier. So you can see this. This is a common emitter amplifier with voltage divider biasing. Okay. Similarly, in MOSFET, what amplifier we will use? We will make use of common source amplifier. Okay. Now, what is the advantage of this Colpit oscillator over Hartley oscillator? Okay. What is the main advantage? The main advantage is at high frequency, the reactance of capacitor, which is 1 by omega C, is very low. If reactance of capacitor is low, the high frequency signal will get a low reactance path or low impedance path. So what we can say? High frequency signal get low impedance path. In the feedback, the high frequency signal will have low impedance path, and hence at high frequency the response will be more sinusoidal. So that is the disadvantage of Hartley oscillator, was that it was unable to generate sinusoidal signal. The signal had harmonics and distortion, but here at high frequency the signal will be smoother and it will be more sinusoidal. Okay. It is also a variable frequency oscillator. How it is variable frequency? Here we are writing that operating frequency is 1 by 2 pi under root L into C equivalent. As you can see, inductance is variable, so we can vary the operating frequency of the circuit. Okay. It is used where wide range of frequency is required. Okay. Then basically it is mostly used where high and low temperature occur frequently. That means where the temperature variation is large, sometimes the temperature may be high, sometimes the temperature may be low, this type of oscillator is preferable. Okay. So that is what we are saying about this oscillator. The third oscillator in LC oscillator is called as the clap oscillator. So clap oscillator is nothing but modified version of this Colpit oscillator. Okay. How it is modified? That we are using a variable capacitor C3. Okay. So we have modified by adding a new capacitor C3 in order to improve the frequency stability. Okay. So by adding C3, we will later on understand what is frequency stability. So by adding C3, frequency stability is improved. Okay. So we just want to improve the frequency stability of the circuit, and that is why we are using C3. Okay. Now what is the operating frequency of this circuit? Is 1 by 2 pi under root L C3. Now what happens is C3 dominates C1 and C2. If C3 dominates C1 and C2, so that is, then what happens basically, operating frequency becomes independent of C1 and C2. So that is desirable. What I want actually is operating frequency should depend on lesser number of parameter so that the frequency almost remain same. But if it depends on more number of parameter, then what will happen? The frequency can change if any parameter varies. That is why in clap parameter we are using an additional capacitance that will dominate the earlier capacitors. Okay. The last oscillator we study is called as the crystal oscillator. Now earlier we were making use of tank circuit in order to generate the oscillation, but crystal oscillator uses mechanical vibrations. Okay, that is, we are not going with the electrical circuit, but we are going with mechanical vibration, and that is being used to generate electrical oscillation. Now what is the main reason behind going for crystal oscillator is high degree of frequency stability. What is meant by frequency stability actually? That with respect to change in environmental condition, the operating frequency of the system should not change. That is, no matter what happens, the frequency of the system should remain same as it is, and that is called as the frequency stability. Okay. So that is why crystal oscillators will be used in application where we need a constant frequency. As if you have studied microprocessor, there to generate the clock signal. To generate clock signal, we always make use of the crystal oscillator. Okay. Now, what is the basic principle of this crystal oscillator? So in crystal oscillator, what happens? When mechanical strain means deformity, is applied. When mechanical strain is applied, stress is developed. Always remember, strain is the reason for development of stress. Due to this development of stress, the electric dipoles become aligned and generate electric field and voltage. So that is what a crystal oscillator is based on. We call as piezoelectric effect. Piezoelectric effect means electricity or electric effect is generated when mechanical stress or pressure is applied. Piezo, by meaning of piezo, we mean to say pressure. So under mechanical pressure, electricity is generated, and that is called as the piezoelectric effect. Okay. So this crystal oscillator is always based on the piezoelectric effect. So as you can see, in crystal oscillator we have a piezoelectric material such as quartz. So what are the piezoelectric material which are commonly used or naturally occurring? Piezoelectric materials which naturally occur are two material, quartz and Rochelle salt. These two materials are commonly occurring piezoelectric material. So what we have done, between the plates of capacitor, we have placed a piezoelectric material which also acts as a dielectric. So that is the construction of your crystal oscillator. And if you see from the outside, it will have two axes. One is the mechanical axis. Mechanical axis is where your pressure will be applied, and electrical axis where we can observe the voltage. So along electrical axis voltage will be produced, and along mechanical axis we will apply stress or strain. Now what we do is, we model this piezoelectric crystal by means of an equivalent electrical circuit. Okay, I want to represent it in terms of network analysis. So what I'll do, see the circuit. First we have RLC and then a capacitor in parallel to it. RLC, and suppose this is C0. Now how I am drawing this circuit? What does each parameter represent? R represents damping or internal losses, because when mechanical crystal will vibrate, the oscillation will be damped out due to internal losses. Then C is the stiffness, which is also equal to 1 by K. K is actually called as the spring constant. In any mechanical material, there is always a degree of stiffness, that is, it cannot be compressed or stretched without opposition, and that is called as the stiffness. And L represents mass of crystal. L represents the inertia or mass of the crystal, and C0 is actually the capacitance between anode and cathode, because I told you it is also working as a capacitor. The anode and cathode are two plates of the capacitor between which a dielectric is placed, so it is also working as capacitor, and capacitance between anode and cathode is given by C0. Okay, so RLC are not actual parameters, but they indicate certain physical phenomena inside the crystal. But C0 is actually the capacitance between anode and the cathode. Okay. Now since it is a second order circuit, it has two resonant frequencies. Okay. In second order circuit, we will have two resonant frequencies. One in case of series resonance, that is due to RLC circuit, and the second one is due to parallel resonance, in which we will include the effect of C0. So what is the series resonance frequency? It is 1 by 2 pi under root LC. What about parallel? 1 by 2 pi under root L into C equivalent. What is the C equivalent? C into C0 by C plus C0. Because in this circuit, C and C0 will come in series. Okay, that is your parallel frequency. Now C equivalent is actually less than C. If it is less than C, it means the denominator is less in FP. So you can say FP is greater than Fs. So now if you plot the impedance of the circuit with respect to frequency, if we plot impedance, if I plot mod Z versus frequency, frequency is your F, then how does the curve look like? It looks like this. Okay, this first frequency is your Fs, series frequency, in which impedance is maximum. In parallel frequency, admittance is minimum or impedance is maximum. In series resonance, at resonance impedance is minimum. In parallel resonance, at resonance impedance is maximum. Here the behavior of circuit is capacitive, here it is inductive, and then again capacitive. Okay, so these are the two resonance frequency at which we can say that the crystal oscillates. Okay, and this parallel resonance is also called as your anti-resonance. Why anti-resonance? Because impedance is becoming maximum at this resonance frequency. Now, what are the features of crystal oscillator? It has fixed frequency. Now this frequency always lies between Fs and Fp. The frequency is fixed and it will lie between Fs and Fp. Okay. It is simplest RF oscillator because we have just taken a piezoelectric crystal. We don't have any circuit components. The frequency of oscillation, if we represent using F0, is inversely proportional to thickness of the crystal. Okay, F0 is inversely proportional to the thickness of crystal. Is it fine? It has large quality factor. It has large Q. Okay, and it can generate carrier wave in AM and FM. So that is also one application of the crystal oscillator. Now we have regularly been talking about frequency stability. What does it mean by frequency stability? It means that operating frequency should not change with environmental conditions. That is, no matter what are the external conditions or operating condition, the operating frequency must be same. For this we define a figure of merit. Figure of merit means a parameter by which we can judge the performance. Okay, figure of merit for any system means a parameter by which you can judge the merits and demerits of such a device, or you can judge the performance. So what is the figure of merit of this crystal? It is d theta by d omega. For any crystal it is d theta by d omega, where theta is phase angle of amplifier. Okay, now suppose we see for crystal oscillator at Fs minus the nature is capacitive, at Fs plus the nature is inductive. So what will be the phase for capacitive behavior? For capacitive behavior phase is almost minus 90. For inductive behavior phase is almost 90 degree. So what is FOM? Theta inductive minus theta capacitive upon frequency of inductive Fs plus and Fs minus. Now these two frequencies are very close. If they are very close, it will tend to infinity, or you can say highly stable circuit. So what I mean to say here is that if the variation of phase with frequency is very large, like this, if it is very large, the variation of phase, this is the variation of phase and this is the variation of frequency, then system will be highly frequency stable. That is, for small change in frequency, there must be large change in the phase of the system, and then you can say that the system is highly stable. So if we summarize, what we have to remember, in Hartley oscillator we have 2 inductor and 1 capacitor. So the frequency of oscillation is 1 by 2 pi under root C into L equivalent. In Colpit oscillator we have 2 capacitor and 1 inductor, so 1 by 2 pi under root L into C equivalent. In Clap oscillator frequency is 1 by 2 pi under root L C3. So it makes it independent of C1 and C2. It is modified version of Colpit oscillator. And then if I summarize all the oscillator that we have studied, so first is RC phase shift. It can generate frequencies from 1 Hz to 10 megahertz. Okay. Then VN bridge. It can generate from 1 Hz to 1 megahertz. Okay. Then Colpit, 10 kilohertz to 100 megahertz. Hartley, same as Colpit, but Colpit is more stable at high frequency. Then Clap oscillator. Clap oscillator is also same. It is just the modified version of Colpit oscillator. So if you arrange in the order of stability, Hartley oscillator is least stable and Clap oscillator is most stable. So why we were moving from Hartley to Clap oscillator? So we were trying to increase the stability of the system. Okay. So remember this thing and a vague idea of the range of frequency, so that if it is directly asked in objective question, you can mark the answer. So these are general type of oscillator, and in the next lecture we will see how to generate oscillator using positive feedback in op-amp, which is also called as the Schmitt trigger. That we will cover in the next video. Thank you. Hi guys, in the previous few lectures what we have covered is, we have covered two type of oscillator, RC oscillator and LC oscillator. Now both these type of oscillators are called as harmonic oscillator because they generate sinusoidal oscillation. So in this video we will be studying a different type of oscillator that is called as multi-vibrator, which is a relaxation oscillator and is used to generate waveforms such as square wave, triangular wave and so on. Now first thing first, what is the meaning of a multi-vibrator? Multi-vibrator is a device that oscillates or vibrates between two or more states. Okay. So that is, it is vibrating it between multiple states, and that is why it is called as a multi-vibrator. Now multi-vibrator is basically divided into three categories. The first one is called as astable multi-vibrator. Astable means that it has no stable state. Suppose it has two states from digital, suppose 0 and 1, then none of the state is stable, so it will keep on oscillating between the two states. It will go from 0 to 1 and then it will go from 1 to 0. So it will keep on oscillating between the two states. It will go by itself from one state to the other. It means it does not require any input signal. It will change its state on its own. You don't need to apply any sort of input signal. The second one is called as monostable multi-vibrator. It has one stable state. So let me take an example. Suppose 1 is stable and 0 is unstable. Then it will go from 0 to 1 by its own. But in order to send it from 1 to 0, you need to apply an input. So to go from stable to unstable state, you will need an input signal. But to go from unstable to stable state, we don't need any input signal, and that is called as monostable multi-vibrator. The third one is called as bistable multivibrator. That means it has two stable states, that is both the states are stable. So to go from 0 to 1 also you need to apply an input, and to go from 1 to 0 also you need to apply an input. That means a stable multivibrator does not need any input. Monostable needs input for one transition but does not need any input for the other transition, and bistable needs the input signal for both the transition from low to high as well as from high to low. It needs input signal for both the transition. Now we will first talk about Schmitt trigger. Schmitt trigger is also called as bistable multivibrator. Now what is Schmitt trigger actually? It is op-amp in positive feedback configuration which will work as bistable multivibrator. Bistable means you will need to apply an input in order to change the state of the multivibrator. In order to send it from low to high or from high to low, in both the cases you will need to apply the input. Now how we will show the feedback? The feedback must be from at the positive terminal because we are using positive feedback. That is RF and R1. Okay. That is called as your Schmitt trigger, in which we are feeding the output back to the non-inverting terminal of the input, or we are applying positive feedback. Now Schmitt trigger are basically divided into two categories: inverting Schmitt trigger and the second one non-inverting Schmitt trigger. Inverting Schmitt trigger means input is applied at the inverting terminal. Non-inverting Schmitt trigger means input is applied at the non-inverting terminal. Okay. So it depends where you are applying the input signal. That way you can call the Schmitt trigger either as inverting or as non-inverting. So let us first start with the inverting Schmitt trigger. See. In inverting Schmitt trigger, I have applied the input signal at the inverting terminal and the non-inverting terminal is grounded. And we are connecting the feedback at the non-inverting terminal. Now first thing first, the current at the input terminal is 0 ampere. Okay. That means these two are in series. The voltage of this terminal is V reference. So what is V reference? It is V0. I am applying potential division R2 by R1 plus R2. Okay. Now, what you need to do in such kind of application of Schmitt trigger, how do you analyze this? You first assume case 1. Assume that V0 is plus Vsat. In negative feedback only V0 does not saturate, but in positive feedback the gain will increase, because in positive feedback what is the gain? A upon 1 minus A beta. If the gain is very high, then op-amp will saturate. So output can only have two values, either Vsat or minus Vsat. Remember this thing. In positive feedback, the output always saturates. So we can only have two values, either plus Vsat or minus Vsat. So case 1, I am assuming that output is plus Vsat. In that case, what is V reference? Vsat into R2 by R1 plus R2. That is the reference voltage. Now see, what is the voltage of negative terminal? It is input voltage. If positive terminal voltage is greater than negative terminal voltage, Then by means of comparator you can say V0 is Vsat. That means Vsat R2 by R1 plus R2 is greater than Vin. Or let me call it as Vin less than beta Vsat. This is actually V reference is the feedback voltage. What is the ratio of feedback voltage and the output voltage? The ratio of feedback and output voltage is beta, which is here R2 by R1 plus R2. So I am calling it as beta. If Vin is less than beta Vsat, output remains at Vsat. Now take the second case. If V negative is greater than V positive, voltage of inverting terminal is more than non-inverting terminal, V0 is minus Vsat. So negative terminal voltage is Vin is greater than positive terminal voltage, which is beta Vsat. Then V0 becomes minus Vsat. So I will say as Vn goes above beta Vsat, V0 switches from Vsat to minus Vsat. So output will switch from plus V saturation to minus V saturation if you increase the input voltage above beta Vsat. So this beta Vsat is called as UTP or upper triggering point. That is the triggering voltage, that is the level of input voltage above which the output will switch. So triggering point is the level of the input voltage at which output will switch. Let us see case number 2. Case 2. Assume V0 equal to minus Vsat. If V0 is minus Vsat, V reference, which is V0 R2 by R1 plus R2, will become minus Vsat R2 by R1 plus R2. This factor R2 by R1 plus R2 I called as beta. So minus beta Vsat. Now, if this negative terminal voltage is less than positive terminal voltage, V0 will remain as minus Vsat. Because whenever negative terminal voltage is less, V0 is minus Vsat. So V negative is Vin is less than minus beta Vsat, then output remains as minus Vsat. But if negative terminal voltage is greater than positive terminal voltage, that is Vin is greater than beta minus beta Vsat, the output becomes Vsat. So V0 switches from minus Vsat to Vsat. Okay. So if input goes above minus beta Vsat, then output will switch from minus Vsat to plus Vsat. So if I want to draw it on a curve, or if I want to draw the transfer characteristic, then I want to have a curve between V0 and Vin. This minus beta Vsat in our case is called as LTP, lower triggering point. That is the triggering voltage at which output will change, but it is less than beta Vsat, so it is lower triggering point. Beta Vsat is higher, so it is upper triggering point. So this beta Vsat is actually the limit for Vin. So on the axis of Vin, I will show two voltages. One voltage will be UTP, other voltage will be LTP. But V0 can have two levels, Vsat and minus Vsat. So what we said earlier, if Vin goes above beta Vsat or UTP, then output will go from Vsat to minus Vsat. If input goes above UTP, the output will go from Vsat to minus Vsat if it tries to go above UTP. Okay. And we said if input goes below, actually these conditions are opposite. If input goes below minus beta Vsat, if input goes below minus beta Vsat, output will switch from minus to plus. So it will go like this. It will switch from minus to plus if input goes below LTP. So we show the curve like this. Okay. Now additionally, what we have to do is, see, if input stays below minus beta Vsat, output will remain at minus Vsat. So if input goes below LTP, the output will remain at minus Vsat. Sorry, if it stays above minus beta Vsat, if input is more than minus beta Vsat, V0 remains minus Vsat. So LTP is minus beta Vsat. So what I am saying, if input is more than minus beta Vsat, output will remain at minus Vsat. So we will show like this. That means if input is above LTP, the output will remain at minus Vsat. Same way, see here, if input stays below beta Vsat, then output remains at Vsat. If input stays below beta Vsat, this is beta Vsat. If input lies to the left, then output will remain at Vsat, like this. So it means if you try to go above UTP, output will switch from plus to minus. If you try to go below LTP, it will switch from minus to plus. This is called as hysteresis curve, and this width is called as hysteresis width, and this width is 2 beta Vsat. Okay, hysteresis width is the 2 beta Vsat, which is the difference between UTP and LTP. Same way, if I go by waveform, suppose I have a sinusoidal signal like this, and we have two triggering points. One is UTP and the other is LTP. So what we know about the output? If input goes above UTP, output will go from Vsat to minus Vsat. So here input goes above UTP, output goes from minus Vsat to plus Vsat to minus Vsat. Then we say if input goes below minus beta Vsat is this. If input goes below minus beta Vsat, output will go from minus to plus. If input goes below minus beta Vsat, output will go from minus to plus. Then if input goes above UTP, output will go from plus to minus. Then below LTP, minus to plus. So that will be the waveform of V0. If you try and go above UTP, then output will switch. And if you try to go below LTP, then also output will switch. That means in order to switch from plus Vsat to minus Vsat or from minus Vsat to plus Vsat, you need to change the input signal. Now suppose I modified the inverting Schmitt trigger like I am drawing now. In inverting Schmitt trigger, at the inverting terminal we have input. At non-inverting terminal we have R1, R2, and instead of grounding we are applying a reference voltage Vref. Okay, I have not grounded the positive terminal. Now what happens if you want to find the voltage of the positive terminal? Then V plus is determined by superposition. How to determine V plus by superposition? First of all, ground this V reference. Then V positive will be V naught. These two will be in series always. There is no current here. It will be V naught R2 by R1 plus R2. Then in the next case, in order to apply superposition, take V reference here and ground V naught. Then V positive will be the voltage across R1. Because we have to observe this voltage with respect to ground, now R1 is connected between V positive and ground. So if you again apply voltage division, you will say V reference R1 over R1 plus R2. That is the voltage of positive terminal. Now what you have to do, in order to find UTP and LTP, you have to assume V naught first as V set. In that case, the positive terminal voltage is V set R2 over R1 plus R2 plus V ref R1 over R1 plus R2, and negative terminal voltage is V in. So what I will say, if negative terminal voltage is greater than positive terminal voltage, V naught will become minus V set. That means if input voltage is greater than V set R2 by R1 plus R2 plus V ref R1 by R1 plus R2, then output will switch from plus V set to minus V set. R2 by R1 plus R2 we called as beta. So beta V set plus V reference R1 by R1 plus R2. I will call it as UTP. Similarly, now if you assume V naught as minus V set, then positive terminal voltage will be, this term is beta minus beta V set plus V reference R1 by R1 plus R2. Now you will say, if negative terminal voltage V in is less than positive terminal voltage, then V naught will switch to V set. So this voltage will be called as LTP. So now we have find out UTP and LTP. Earlier UTP was beta V set, LTP was minus beta V set. Now both have a term in addition, which is V reference R1 by R1 plus R2, which means if you draw the transfer characteristic, both UTP and LTP have an additional term, which is V reference into R1 by R1 plus R2. That means if both have certain additional term, both will be shifted to the right. Okay. So this will be your UTP, this will be your LTP. But if you find out UTP minus LTP, which is called as hysteresis width, UTP minus LTP will be same as 2 beta V set, because this term of V reference will get cancelled. So hysteresis width remains same, but by applying reference voltage, what happens? The curve will shift either to the right or to the left depending upon polarity of the reference voltage. Are you getting my point? So what happens if we apply reference voltage? We can shift the hysteresis curve to right or left depending upon polarity of reference voltage. Next category of Schmitt trigger is the non-inverting Schmitt trigger. Now see that inverting terminal is grounded and non-inverting terminal is connected to Vin. So now what will happen, how we will analyze this circuit? We have to find the positive terminal voltage. Now again there are two sources, so we will apply superposition. Find V positive by superposition. So first make V naught equal to 0. Okay, if you make V naught equal to 0, then what will be the value of V plus? It will be V in, and we will consider then the voltage across R1, because we always need to find the voltage of this node with respect to ground. So which terminal are you grounding? V naught. So if you are grounding V naught, you will find the voltage across R1, R1 over R1 plus R2. Secondly, you will make V in equal to 0. If you ground this terminal, then you will take voltage across R2. So it is V naught R2 by R1 plus R2. By superposition, what I can say, V positive is V in into R1 over R1 plus R2 plus V naught R2 over R1 plus R2. Okay. Now, what will happen is, again if you want to analyze this circuit, what you have to do, first let me simplify this expression. I will say R2 over R1 plus R2. 1 minute. R1 we will take common. So it will be V in plus R2 by R1 V naught. Now I told you, whenever you are analyzing a Schmidt trigger, what you have to do, you have to assume two cases. One in which V naught is plus Vsat and the other in which V naught is minus Vsat. So case 1, V naught is Vsat. In that case, what is the positive terminal voltage? R1 by R1 plus R2 V in plus R2 by R1 Vsat. This R2 by R1 Vsat I will call as beta Vsat. But remember, in both the circuits the value of beta is different. Earlier it was R2 by R1 plus R2, now it is R2 by R1. Okay. Now, the voltage of negative terminal is directly 0, it is grounded. So what you will say? If V positive is greater than V negative, output will remain at Vset. That is V in plus beta Vsat greater than 0, or V in greater than minus beta Vsat, then V naught is Vset. But if positive terminal voltage is less than negative, output will switch. What is positive terminal voltage? V in plus beta Vsat is less than 0. So V in is less than minus beta Vsat. In that case, output switches. So this voltage will be called as LTP. So if input goes below LTP, the output will switch from plus Vsat to minus Vsat. Okay. Now, if you take case number 2, V naught as minus Vsat, then what is V positive? It is R1 by R1 plus R2 V in minus beta Vsat. Again take, if V positive is greater than V negative, then V naught will become Vsat. What is V positive? V in minus beta Vsat is greater than 0, or you can say V in greater than beta Vset. So this will be called as UTP. In that case, V0 will switch from minus Vset to plus Vset. But if positive terminal voltage is less than negative, Vin minus beta Vset is less than 0, or you can say Vin is less than beta Vset, then output will remain at minus Vset. So if you try to go above UTP, output will go from minus to plus. If you try to go below LTP, then output will go from plus to minus. So if you try and draw the transfer characteristics, so on y-axis we have 2 points. What are the 2 points? Vsat and minus Vsat. And on x-axis we have 2 points UTP and LTP. So what we have seen, if we try to go above UTP, if you go above UTP, output will go from minus Vsat to plus Vsat. So above UTP, output will go from minus Vsat to plus Vsat, and below LTP it will go from plus Vsat to minus Vsat. So if you complete the curve, it will come in anti-clockwise direction like this. But if you see, if we stay below UTP, output remains at minus Vsat. If we stay below UTP, output will remain at minus Vsat. Or if we stay above LTP, output will remain at Vsat. So that is the complete hysteresis curve. And again the width, this hysteresis width is 2 beta Vsat, but in our case beta is how much? It is R2 by R1. So beta changes in both the cases, but what also changes is the orientation of curve. In inverting Schmidt trigger, the curve was clockwise. In non-inverting Schmidt trigger, the curve is counter clockwise. Okay. So if I summarize what we have covered in this video, I have told you about the different types of multivibrators, that there are 3 categories: astable, monostable, bistable. Then we have seen Schmidt trigger, that it is of 2 categories: inverting and non-inverting. Here the LTP was minus beta Vsat, UTP was beta Vsat, where beta was how much? R2 over R1 plus R2. In non-inverting, beta became R2 by R1, but the concept remained the same. And I defined that the hysteresis width is the difference between UTP and LTP. And also I gave one more thing, that in inverting Schmidt trigger, the hysteresis curve is clockwise, whereas in non-inverting it is counter clockwise. Okay. So that is all about Schmidt trigger. So how you have to analyze? Just find out the voltage of both the input terminals of op-amp and compare the voltages in order to find the output. So that is how we analyze the Schmidt trigger. Okay. So in the next lecture I will show you application of Schmidt trigger, but this is all about the Schmidt trigger. Thank you. Hi guys, in the previous video we started with the topic of multi-vibrators. In multi-vibrator I told you that they are of three categories: astable, monostable and bistable. In astable what was the case? It did not have any stable state, so it keeps on oscillating between two states. In monostable it had one stable state, so it went from stable to unstable by means of input signal and from unstable to stable on its own. In bistable it had both the stable states, so it needed an input signal to switch the state from one state to the other. Then I introduced to you the concept of Schmitt trigger, which is also called as bistable multi-vibrator. And I told you that the Schmitt trigger is divided into two categories. One is called as the inverting Schmitt trigger and the other is called as the non-inverting Schmitt trigger. Okay. Now what happens in inverting Schmitt trigger? The hysteresis curve was clockwise. In non-inverting it was anti-clockwise. Here beta was R2 over R1 plus R2. Here beta was R2 by R1. UTP and LTP in both the cases was upper triggering point was beta Vset and LTP was minus beta Vset. I told how do we analyze a Schmitt trigger? Always we assume V0 as plus Vsat and minus Vsat and then check the value of input voltage at which output will switch from one state to the other. And I told when we apply a second source called as reference voltage, the hysteresis curve will shift to right or left, but the hysteresis width and height will remain same. So reference voltage can only provide left shift or right shift in the hysteresis curve. So in this video what we'll do is, we know the Schmitt trigger, so we will understand the application of Schmitt trigger, how we will be constructing different circuits based on Schmitt trigger. That we'll see in this video. So the first application is the triangle wave generator. Now if you see the first part of this circuit is your non-inverting Schmitt trigger. Okay. What is the input voltage for this circuit? The input voltage of this circuit is actually the output voltage V0. Suppose this voltage is V. The second part of this circuit is your integrator. That means if you want to generate a triangle wave, then we must first generate a square wave, and if we integrate a square wave, what we will get is the triangular wave. So we will try to generate square wave using the non-inverting Schmitt trigger, and then we will integrate this square wave in order to get the triangle wave. Now, what is the output of integrator? We derived in the chapter based on op-amp. V0 was minus 1 by RC integral V dt. That was the value of the output voltage of integrator. Okay. So what I will do is, in order to analyze this circuit, let me say case 1. Suppose the output of non-inverting Schmitt trigger V is Vset. Then what is V0? V0 is minus 1 by RC integral Vsat into dt. So it is minus Vsat by RC into T. Now what is the working of non-inverting Schmitt trigger? For non-inverting Schmitt trigger, what we say, if input voltage, if Vin becomes greater than beta Vset, then V switches from minus Vsat to plus Vsat. That I derived for you in the last lecture. And I also told if Vin goes below minus Vsat, minus beta Vsat, V switches from Vsat to minus Vsat. Okay. Now see, here the input voltage is actually the output voltage V0. So what I will say? I will say if V0 goes below minus beta Vsat, then V switches from Vsat to minus Vsat. So what I have done is, in this statement, I have just substituted Vin by V0 because Vin is actually V0. Now this is your V0. So what I am saying, this V0 is linearly decreasing, and if it goes below minus beta Vsat, the V which we assume to be Vsat will switch from Vsat to minus Vsat. Okay. So what I will say, V0 is minus Vsat into T by RC. If it becomes minus beta Vsat, then V will switch from Vsat to minus Vsat. So what is the time? T1. T1 is actually minus beta, plus beta RC. Okay. That is your T1. So at this time, V will switch from Vsat to minus Vsat. Now I will take case number 2. Now V is your minus Vsat. If V is your minus Vsat, what is V0? V0 is minus 1 by RC V dt. Or you can say dV0 by dt is minus V by RC. So you can write like this, dV0 is minus V by RC dt. Integrate both the sides. Okay. Integrate both the sides. What is initial value of V0? In previous case, V0 became minus beta Vsat. So what is the initial value? Minus beta Vsat at time t equal to t1. Then V0 becomes V0 at time t. So V0 plus beta Vsat, V is actually equal to minus Vsat, is minus plus Vsat by RC t minus t1. So V0 is actually minus beta Vsat plus Vsat by RC t minus t1. Now see this first statement. If Vin which is actually V0 goes above beta Vsat, V will switch from minus Vsat to Vsat. So I will say if V0 goes above beta Vsat, V switches from minus Vsat to plus Vsat. So keep the value of V0 as beta Vsat. Suppose this happens at a time t equal to t2. So what is this t2 minus t1 then? It is 2 beta RC. Okay. Where this R is actually R3. Okay. So you can write here as R3C. Here also as R3C. Okay. This much is clear. So now if I go by waveform, let me show you how this waveform will be plotted. See, I will plot two waveforms. One will be for the case of V and other will be the case of V naught. V naught actually have two levels defined, beta V set and here minus beta V set. So I will indicate these two levels on the V naught waveform. Beta V set and the second one minus beta V set. Okay. Now initially what we assumed? We assumed that V is equal to V set. So V naught was linearly decreasing. So initially we assumed that V is actually equal to V set. So V naught initially was 0. It started to linearly decrease. Now as soon as it touches minus beta V set, V will switch from V set to minus V set. V will switch from V set to minus V set. Now when V switches from V set to minus V set, the output starts to linearly increase, and when it linearly increases and when it touches beta V set, output goes from minus V set to V set. So it linearly increases, and when it touches beta V set, V will switch from minus V set to plus V set. Then it will again from case 1, it will start to linearly decrease. So now if you see the waveform at V naught, it is a triangular wave, but at V it is a square wave. This is the time t1, this is the time t2. And what is the difference in the times? It is 2 beta R3C. So this time is actually half of the time period, because full time period is the total one, this. So T by 2 is actually 2 beta R3C, which means time period is 4 beta R3C. Beta is how much for the non-inverting Schmidt trigger? R2 by R1. So what you can say, frequency of this triangular wave is 1 by T. So R1 by 4 R2 R3 C. That will be the frequency of this triangular wave generated. Okay. So that is how you will analyze the circuit of triangle wave generator. No need to memorize this expression, because an identical circuit has a very less chance to be asked in gate. They can ask you a different type of circuit. Moving to the next application, the next one is called as astable multi-vibrator. Now what kind of Schmidt trigger it is? If you call VC as VC is V in, then input is connected. Input is connected at inverting terminal, and hence it is inverting Schmidt trigger. Okay. So it is an example of inverting Schmidt trigger. The non-inverting terminal is grounded and we are connecting capacitor voltage as the input voltage at the inverting terminal. Okay. So now how do I analyze this circuit? First of all, understand that there is no current going at the negative terminal. So this R and C are in series. R and C are in series with V0 acting as source. So it is a series RC circuit in which your source is what? Source is V0. Now I have always told you how to analyze the circuits based on Schmidt trigger. Assume the value of V0 as Vset and minus Vset. So let me assume case 1. V0 is Vsat and initially Vc is 0. Okay. If this V0 is Vsat, then this RC circuit acts as a series circuit. See like this. This circuit is a series RC circuit with source as V0. Like this. Now if I want to find the value of Vc infinity, what is the steady state value? Check this circuit. It is V0, which is Vsat. Initially Vc is 0. So how you will write the equation of Vct? Vc infinity plus Vc 0 minus infinity e to the power minus t by tau. So Vsat 1 minus e to the power minus t by tau. That is the value of Vc. Now here there is 0 current. So what is the positive terminal voltage? For positive terminal voltage you can apply potential division. So you can always say it is V0 into R2 by R1 plus R2. Since 0 ampere current is going into the op amp, R1 and R2 are connected in series. And we can only apply potential division when connection is in series. Now V0 is Vsat. So Vp is Vsat R2 over R1 plus R2, or you can call it as beta Vsat. Now see, the capacitor voltage, which is also the voltage of negative terminal, is increasing. It is increasing towards Vsat. But if Vp is greater than Vn, V0 will remain Vsat. But now Vn is increasing. It is increasing towards Vsat. And here beta is R2 by R1 plus R2. It is less than 1. So beta Vsat is less than Vsat. Now think like this. The voltage of positive terminal of op amp is beta Vsat, which is less than Vsat. But voltage of inverting terminal is increasing towards Vsat. At some time it will cross beta Vsat. And when it crosses beta Vsat, that is when Vn becomes greater than Vp, V0 will switch from minus Vsat. So V0 switches from Vsat to minus Vsat. So as capacitor charges towards Vsat, at some point it overtakes the positive terminal voltage and it becomes more than positive terminal voltage. At that time V0 will switch. Now suppose I want to find that time. For that what I will do, I will keep V0 as beta Vsat, Vc as beta Vsat. Okay. And I will call that time as T1. So Vsat gets cancelled. So what is T1? T1 is tau ln 1 by 1 minus beta. Okay. That will be the time T1. Is it fine? I have just solved this equation and nothing more. Now see. Now we will go to case 2. Now V0 becomes minus Vsat. Since V0 switched from Vsat to minus Vsat, now V0 is minus Vsat. In that case, Vp was V0 R2 by R1 plus R2. It becomes minus beta Vsat. But now capacitor became charged up to beta Vsat. And Vc infinity, if you see this circuit, Vc infinity is always V0, but now V0 is what? Minus Vsat. So you can write VC equation. It is VC infinity plus VC 0 minus VC infinity e to the power minus t by tau. So minus Vsat plus beta plus 1 Vsat e to the power minus t by tau. Now this Vc is actually the voltage of the inverting terminal of op amp. And what is the voltage of non-inverting terminal is minus beta Vsat. So now what I will say, if the negative terminal voltage is greater than positive terminal voltage, V0 will stay at minus Vsat. But if negative terminal voltage becomes less than positive terminal voltage, V0 will become Vsat. So I will say V0 switches from minus Vsat to plus Vsat. So let us see at what time does it occur. So I will keep Vn as minus beta Vsat. So it is minus Vsat plus beta plus 1 Vsat e to the power minus t by tau. Let me call it as T2. So Vsat gets cancelled from both the sides. If you take this 1 on the left hand side, 1 minus beta equal to 1 plus beta e to the power minus T2 by tau. From here if you solve, T2 is tau ln 1 plus beta over 1 minus beta. That is the time at which output again switches from minus Vsat to plus Vsat. So as you can see in this circuit, output itself is switching from one state to the other, and hence it is called as a stable multi-vibrator. Now if I talk about the waveform, of the circuit, so I will draw two waveforms. One is for capacitor voltage and other is for output voltage. Okay, this is V0, and then I will also draw Vc. The x-axis is time, this is Vc. Now see, initially we assumed V0 is Vsat, and I told you capacitor always tries to charge towards value of V0. Capacitor tries to charge up to Vsat, but in between we have a level beta Vsat and minus beta Vsat. This level is Vsat and minus Vsat. Capacitor always tries to charge up to V0 or Vsat, but in between it finds a level beta Vsat. See what happens. Capacitor starts charging from 0. It tries to go till Vsat, but in between it finds beta Vsat. As soon as it finds beta Vsat, then what happens? The output V0 switches from Vsat to minus Vsat. Now capacitor will try to go till minus Vsat, but it cannot go till minus Vsat as soon as it reaches minus beta Vsat. As soon as it reaches minus beta Vsat, the output will again switch from minus Vsat to Vsat. As I told here, output goes from minus Vsat to Vsat as soon as capacitor voltage becomes minus beta Vsat. Then capacitor will charge from minus beta Vsat to beta Vsat. So capacitor waveform will be exponential, whereas output waveform will be square wave. So in this manner, we can generate a square wave. This will be the total time period t. We don't consider this interval. Why we don't consider? Because capacitor starts charging from 0. So this is called as the transient waveform. But when capacitor oscillates between beta Vsat and minus beta Vsat, this is called as steady state. So we have found out this interval, this one, that is actually t by 2. So what is time period t? T is 2 RC ln 1 minus beta by, 1 plus beta by 1 minus beta. And once you have the time period, you can also find the frequency, which is 1 by time period. Okay. So just solve in one interval and then double that interval in order to find the period of the waveform. So what I have told, the time period is 2 RC log 1 plus beta by 1 minus beta, where beta is how much? R2 over R1 plus R2. And frequency of oscillation is 1 by t. Okay. So you don't have to memorize this expression. Just remember how did I analyze this circuit. So what I did, I actually analyzed it using transient analysis. I assumed initial value of V0 and then charged the capacitor so that V0 will change its state. But remember, in astable multivibrator, V0 will act as a source for the series RC circuit. Okay. The third category is the monostable multivibrator. Now this monostable multivibrator is also called as mono-short multivibrator or one-shot multivibrator. So what I have told you about monostable multivibrator, that it has one stable state, that is it will go from unstable to stable state by its own. Okay, but it will go from stable to unstable state only when you apply the input. Okay, so what I have told about monostable, it goes from unstable to stable by its own, but it goes from stable to unstable by applying an input. Okay, see what will happen. Actually what will happen is, initially suppose diode is on. If the diode is on, what is the voltage of negative terminal? It is 0.7 volt. Okay, and you push this switch, we push trigger, then positive terminal voltage becomes 0. In that case, negative terminal voltage is greater than positive terminal voltage and output will become minus Vsat. But remember one thing, this switch is such that we will push this switch and suddenly we will switch it off. Like the case of a button, if you see your remote, if you push the power button, you will remove the hand immediately. So it will come back to its original position. That is, trigger is only pushed momentarily. Trigger is only pushed momentarily, then it will again be turned off. Okay, but due to that momentary push, V0 becomes minus Vsat. Now we know the current here is 0 ampere. If the current here is 0 ampere, R1 and R2 are in series. So we can find out Vp. Vp can be found out by voltage division, V0 into R2 by R1 plus R2. So minus Vsat R2 by R1 plus R2. or you can say minus beta Vset. But since V0 becomes minus Vset, due to negative voltage, diode turns off. V0 is minus Vset, so diode turns off. Now see this circuit, it becomes a RC circuit, just like the case of R-stable multivibrator. So RC circuit or series RC circuit is formed. What is the supply for that circuit? The supply for that circuit is V0. Just like R-stable multivibrator, V0 will act as a source for RC circuit. So what will happen? Initially capacitor is discharged. How I am saying this? If we take it as an ideal diode, what is the voltage drop across the diode? The voltage drop across the diode is 0. That means initial capacitor voltage is 0. Here I have taken 0.7 just to show that the output will become minus Vsat. But if you take ideal diode, the capacitor voltage will be 0 because initially diode was on. So initially capacitor voltage is 0. What is steady state capacitor voltage? It is V0, which is minus Vset. So how you will write VCT? Vc infinity plus 0 minus infinity e to the power minus t by tau. So minus Vsat 1 minus e to the power minus t by tau. This is actually the voltage of negative terminal. Now see, if positive terminal voltage is less than negative terminal voltage, V0 will remain at minus Vset. But actually the capacitor voltage is decaying. The capacitor voltage is decaying towards minus Vset. But positive terminal voltage is minus beta Vset. So at some time it will cross it. Okay. Capacitor is charging to minus Vsat. So at some time it will cross minus beta Vsat. So if Vn crosses minus beta Vsat, then Vn becomes less than Vp. If Vn becomes less than Vp, V0 becomes Vsat. If V0 becomes Vsat, so let me check the time at which it occurs. Let me call that time as T1. So from here what I will get is T1 is tau log 1 over 1 minus beta. At this time V0 will become plus Vsat. If V0 becomes Vsat, then V0 is positive. If V0 is positive, then capacitors charges towards Vsat. Because capacitor always tries to charge towards V0. But as soon as capacitor voltage becomes positive, as soon as Vc becomes greater than 0, diode becomes forward bias and Vc stays at 0. As soon as this capacitor voltage will become positive, capacitor is charging towards Vsat. So if capacitor starts charging towards Vsat from here, like this, it will cross 0. As soon as it crosses 0, diode becomes forward bias and Vc becomes 0. What about Vp? Vp was V0 into beta. So beta Vsat. Okay, because V0 becomes Vsat. Now the negative terminal voltage is 0, but positive terminal voltage is beta Vsat. So Vp is greater than Vn. So V0 will be Vsat. That means this is the stable state. The circuit will keep on staying in Vsat. It will not leave this state. and that means it is monostable multivibrator. The state of the output Vsat is stable, whereas if you want to make it minus Vsat, you have to push the trigger. Let me show you this by means of waveform. Okay, again I will draw two waveforms, Vc and V0. So first we will see the waveform of V0 and then we will draw Vc. So initially I was saying that circuit is resting in the state of Vsat. Suppose. And diode was forward biased, so capacitor voltage was 0. Suppose at this time trigger is pushed. As soon as trigger is pushed, we saw output switched from Vsat to minus Vsat. And capacitor starts charging. Capacitor starts charging towards minus Vsat. Okay. Capacitor starts charging towards minus Vsat. But as soon as it reaches minus beta Vsat, the output switches from minus Vsat to plus Vsat. Okay. Then due to that, capacitor starts charging towards plus Vsat. But as soon as it crosses 0, capacitor starts charging towards Vsat. As soon as it passes 0, the diode becomes forward bias and the voltage stays at 0. So output will stay in Vsat. So that means when you push the trigger, output becomes minus Vsat for a certain time, let us say t. And then it will come back to Vsat and keep on staying in Vsat until you push the trigger again. So from minus Vsat to plus Vsat is by its own, but from Vsat to minus Vsat we have to push the trigger. So Vsat is your stable state in which it can stay as long as possible, and minus Vsat is unstable state in which it will stay only for short duration. So this T is called as pulse width, which we derived as RC ln 1 over 1 minus beta. So monostable multivibrator is used to generate a pulse of width RC ln 1 over 1 minus beta. So if I summarize what we have covered in this video, we have seen triangle wave generator, which is basically non-inverting Schmitt trigger plus an integrator. Then we saw astable multivibrator. Okay, in this we were generating a square wave using inverting Schmitt trigger. We derived that the time period was 2RC ln 1 plus beta by 1 minus beta, and beta was R2 over R1 plus R2, but it is better to analyze it as a transient circuit. Then we saw monostable multivibrator. Here it generated a pulse of width RC ln 1 over 1 minus beta, and the stable state was Vsat and minus Vsat was unstable. Okay, so that is all about application of the Schmitt trigger. Okay, so these are the oscillators that you can generate using op-amp, or you can also say positive feedback applications of op-amp. This much you need to understand, and if you keep it like circuit analysis, you won't have to memorize any formula. Okay, So this is all from this video. Thank you. Hi guys, in the past few lectures we have been talking about oscillators. So we started with the basic introduction of oscillator, in which we studied about Bar-Hussein criteria. There I told the product of amplifier gain and the feedback factor A into beta must be 1 for sustained oscillations. Then we looked at some of the oscillator like Wien bridge oscillator, like RC phase shift oscillator, Hartley, Colpit, Clap, crystal oscillator, and then the multi-vibrators using op-amps such as Schmidt trigger, R-stable multi-vibrator, monostable multi-vibrator. So what we'll do in this video is, we'll take a look at the problems that are based on the concepts that we have learned so far, and you will understand how to apply all the concepts in problem solving. Okay, so let us start with the first one. We need to find the frequency of oscillation and the value of resistance Rx to sustain the oscillation. Now see this circuit. If you see the feedback, if you see this feedback connected at the positive terminal, then you can identify that it is a RC phase shift oscillator. Okay, this is RC phase shift oscillator. So in order to find out beta, we know beta is actually Vf by V naught. So let me draw the circuit of the feedback. This is our circuit. C, R, R, C. This is your Vf. This is your V naught. Okay. So that is the circuit. So what I'll do is I'll assume a voltage V here. Now, what is the capacitor current IC in this capacitor? IC will be Vf divided by 1 upon SC. That is SC Vf. That is your capacitor current. Then what about this voltage V? If this is IC and we know that there is no current going here, this IC current would be coming here. So what is V? V is actually Vf plus ICR. That is Vf 1 plus SCR. Once we have this, what I will do is I will apply nodal analysis like this. So I will say V minus Vf by R, okay, plus V by R plus V minus V naught over 1 by SC equal to 0. So V minus Vf by R, V minus Vf by R is actually IC, which is SC Vf. V by R is Vf by R plus SC Vf plus V minus V naught by SC is SC Vf 1 plus SCR minus SC V naught. Now take LCM R, 2 SCR Vf. I have added these two terms, plus Vf plus SCR Vf 1 plus SCR equal to SCR V naught. So if you take Vf by V naught, then it will be SCR over SCR square plus 3 SCR plus 1, and that is the value of beta. Okay. So what is the value of beta? SCR divided by SCR square plus 3 SCR plus 1. Now if you convert it into frequency domain, you will replace S by j omega CR by j omega CR whole square plus 3 j omega CR plus 1. Now take the numerator j omega CR into denominator. So j omega CR plus 3 plus 1 by j omega CR. 1 by 3 plus j omega CR minus 1 by omega CR. Now we know that beta must be real. That means the imaginary part of beta must be 0. So in the denominator, the imaginary term must be 0, which means omega will be 1 by RC. So that is the frequency of oscillation in terms of F, 1 by 2 pi RC. Now it is asking us the value of Rx. So this is a non-inverting amplifier because the input is at non-inverting terminal. So what is the amplifier gain? The amplifier gain is 1 plus Rx by R. And by Barkhausen criteria I know A beta must be equal to 1. So at oscillation frequency, imaginary part is 0. So beta is 1 by 3. So that means A by 3 must be 1 or A must be 3, which is 1 plus Rx over R. So you can say Rx equal to 2R. Okay. So that will be the value of Rx in order to have sustained oscillations. Is it fine? So moving on to the next problem, we need to find the value of R in the oscillator circuit such that it oscillates at an angle frequency omega, and we need to find the value of omega and the value of R. Now again see, this is a non-inverting amplifier because input is at the non-inverting terminal. Okay. So if I want to find the value of Vf by V naught, beta we know is Vf by V naught. Suppose the parallel combination of these three is represented by an impedance Z. So what is Vf by V naught? It can be obtained by potential division. It is Z over Z plus R. Now we say that beta must be real. If beta must be real, the imaginary part of beta must be 0. And for imaginary part of beta must be 0, Z must be real. Or you can say imaginary part of Z is 0. Now Z consists of C, L and R. So for Z to be real, L and C must be in resonance. Because if you have gone through network analysis, we know that parallel LC circuit at resonance behaves like a open circuit. In that case only R equal to 1 kilo ohm will remain and hence beta will be real. So what is the resonance frequency? We will have omega equal to 1 by under root LC 1 by under root 10 to the power minus 2 into 10 to the power minus 8. So 10 to the power 5 radian per second. Okay. Now since Z has become real, Z has become equal to 1 kilo ohm. What is beta? Beta is 1 kilo ohm by 1 kilo ohm plus R. And what about amplifier gain? It is actually 1 plus feedback resistance by input resistance, that is 21. And we know that A beta must be equal to 1. So beta must be 1 by 21. Hence R must be 20 kilo ohm. Okay. From here we get the value of R to be 20 kilo ohm. So what I have done? I have first made beta to be real to find the oscillation frequency, and then A beta equal to 1 to find resistance or to find gain. Remember, this is the method that is generally used in oscillator to make beta to be real to find the oscillation frequency. Moving to the next problem, it is asking us to find the nature of oscillator and frequency. So here what we have? We have two capacitor and one inductor. Whenever we have two capacitor and one inductor, it is called as your Colpit oscillator. Okay, but we have constructed this Colpit oscillator by means of BJT. So what is the frequency of Colpit oscillator? 1 by 2 pi under root L into C equivalent. What is C equivalent? Series combination of C1 and C2. So it will be 1 picofarad. So what will be oscillation frequency? 1 by 2 pi 10 to the power minus 5 into 10 to the power minus 12. So it will come out to be 50.33 megahertz. Okay, that is the frequency of this Colpit oscillator. Next one. Consider the ideal op-amp circuit with two diodes having zero cut-in voltage. We need to plot the transfer characteristic. Now if you see, we have input at the inverting terminal and feedback at the non-inverting terminal. It is a inverting Schmitt trigger. Okay, and we know that the Schmitt trigger can have two possible output, Vsat and minus Vsat. So first I'll assume if V0 equal to Vsat, that is 10 volt. This is the saturation voltage. Now due to positive V0, this D2 will turn on and D1 will be off. Okay, because positive voltage when applied at anode of the diode turns on. So this will be the feedback path. So what is the feedback voltage of the positive terminal voltage? By potential division, V0 into 2 by 2 plus 0.5. So how much will it become? 0.8 V0, or you can say 8 volt. Is it fine? Now if you take V0 equal to minus 10 volt, then D1 will be on and D2 will be off, because when we apply negative voltage at the cathode of a diode, then diode turns on. Now this will be the feedback path. So what is positive terminal voltage? V0 into 2 by 2 plus 2. So that means will be 5 volt. Okay, sorry, minus 5. Now if we will say that if V negative, which is equal to V in, becomes greater than 8 volt, then negative terminal voltage is more than positive terminal voltage. V0 will switch to minus 10 volt. So here V0 is switching. Here we will say if V negative equal to V in becomes less than minus 5 volt, then negative terminal voltage is less than positive. In that case, V0 will become 10 volt, and here the output will switch from minus 10 to plus 10. This is again switching. So output is switching when V in becomes less than minus 5 or V in becomes greater than 8 volt. So these are representing the UTP and LTP. So when we will draw the transfer characteristics, what we will do, V0 can have two voltages, 10 volt and minus 10 volt. V in has two levels, 8 volt and minus 5 volt. So we will construct a rectangle first of all. Because in Schmidt trigger we have to draw the hysteresis curve. So what we are saying, if Vin becomes more than 8 volt, output will go from plus 10 to minus 10. So at 8 volt, output goes from plus 10 to minus 10. And at minus 5 volt, output goes from minus 10 to plus 10. So like this, the curve will be clockwise. Okay. So we will show like this. Okay. That means if you are at 10 volt, then no matter how below you go minus 5, you will stay at 10. Similarly, if you are at minus 10, then no matter how much above you go above 8 volt, the output will remain at minus 10. Okay. That is your transfer characteristic. Next one. If the op-amp circuit shown in the figure, the Zener diode clamp the output voltage at plus 5 volt or minus 5. If the switch is opened at t equal to 0, find the time at which V0 changes state. Okay. See. Initially, switch is closed. If the switch is closed, what is the negative terminal voltage? Due to short circuiting of capacitor, it is 10 volt. Now, V0 can be 5 or minus 5. And what is the positive terminal voltage here? By feedback logic, what is the positive terminal voltage? V0 into 1 by 1 plus 4. By voltage division, V0 by 5, that is 1 volt or minus 1 volt. In both the cases, 1 volt or minus 1 volt, V negative is greater than V positive, because 10 volt is much higher than 1 volt or minus 1 volt. If that is happening, negative voltage is higher, V0 will be minus 5 volt. So when the switch is closed, V0 is at minus 5. Now it is saying the switch is opened at t equal to 0. We need to find the time at which V0 will change the state. V0 changing state means V0 going from minus 5 volt to plus 5 volt. That is the meaning of change of state of V0. Okay. So when switch is opened, capacitor starts charging. Now up to what voltage can capacitor charge? Vc infinity. That you can obtain by open circuiting the capacitor, and you will see it is 10 minus 10 up to 20 volt it can charge. And what is the initial capacitor voltage? It is 0. Okay. So now if you write Vc equation, it is Vc infinity plus 0 minus infinity e to the power minus t by tau. So 21 minus e to the power minus t by tau. Now V0 is at minus 5 volt. So what is V positive? V positive is at minus 1 volt. If V positive is at minus 1 volt, we need to find the time at which the negative terminal voltage goes below minus 1. What is the negative terminal voltage by KVL? 10 minus Vc. So minus 10 plus 20 e to the power minus t by tau. Now when V negative will become less than V positive, then V0 will change the state to plus 5 volt. So it is asking the time at which V0 will change the state, and that will be the time when V negative becomes less than minus 1 volt. So we need to find that time. So V negative we will keep as minus 1, minus 10 plus 20 e to the power minus t by tau. So t is tau ln minus tau ln 0.45. So it will come out to be what is tau RC. What is the product of resistance and capacitance? R is 10 to the power 4, capacitance is 10 to the power minus 4. That is 1. So minus ln 0.45. If you substitute the value of ln 0.45 in calculator, it will come out to be 0.798 second. So at this point of time, the state of the output will change. Moving on to the next problem. Consider the phase shift oscillator shown in the figure with parameters C equal to 10 nanofarad and R equal to 4 kilo ohm. We need to find the frequency of oscillation and the value of R2. Now this is basically a RC phase shift oscillator as mentioned in the question, and each op amp is in voltage follower configuration. Now I told you, when we are talking about RC phase shift oscillator, then we cannot multiply the transfer function of each stage due to loading effect. I told you what is loading effect. When current flows between the two stages, it is called as loading effect. In that case, transfer function cannot be multiplied. But in this question, if you see, between every stage of RC, there is a op amp. So op amp is connected. Op amp is connected between the stages. That is true. If op amp is connected between the stages, it causes zero current, or it provides isolation. If it provides isolation, then there is no loading effect. Hence, we can say transfer function can be multiplied. So if you see each stage is like this. How many stages are there? There are 3 stages. Now you will say that this stage is not like this. This is different. But no, it is same, because by virtual ground, what you can say? The voltage of negative and positive terminal is same. So this voltage is 0 volt, or it is grounded. Now you can see this stage is also identical to the previous 2 stages. So what is the transfer function? The transfer function is V2 by V1, which can be obtained by voltage division, R over R plus 1 by SC, that is SCR over 1 plus SCR. Now there are 3 such stages, so we can say the feedback factor is product of the 3 transfer function, or transfer function cube. So SCR cube by SCR cube plus 3 SCR square plus 3 SCR plus 1. That is the feedback factor beta. Now you can simplify this feedback factor by bringing SCR cube from numerator to denominator. Okay. In that case, it will be 1 over 1 plus 3 by SCR plus 3 by SCR square plus 1 by SCR cube. Now if you replace S by j omega, 1 by 3 by j omega CR plus 3 by j omega CR square plus 1 by j omega CR cube. So that is 1 over 1 plus minus j 3 by omega CR minus 3 by omega CR square plus j by omega CR cube. That is the value of beta. Now we know that imaginary part of beta must be 0. In that case, the imaginary term in the denominator must be 0. So 1 by omega CR minus 1 by omega CR cube, this must be 0, sorry, 3 by omega CR. That is 3 by omega CR equal to 1 by omega CR cube. So you can say that omega CR square is 1 by 3. So omega is 1 by RC under root 3. That is the frequency of oscillation. In that case, what is beta? 1 by 1 minus 3 by omega CR square. Now omega CR square is 1 by 3. That is 1 by 1 minus 9 or minus 1 by 8. By Bar-Hussein criteria we know A beta equal to 1, A will be equal to minus 8. And what is the gain of the amplifier? This is an inverting amplifier because input is applied at inverting terminal. Okay. If input is applied at inverting terminal, what is the gain? Minus R2 by R. So R2 is equal to 8R. Is it fine? See how I am saying this is the input. Basically, we have 3 stages like this. This actually is ground. This voltage is connected to V0. So this voltage across the resistance R will be Vf. If this is Vf, this will act as the input to the amplifier. So if it is acting as the input to the amplifier, always remember, in oscillator, the feedback voltage acts as the input to the amplifier. So what is the input? Vf. So what is the gain? Minus R2 by R. So R2 is equal to 8R, and are we given the value of R? R is 4 kilo ohm. If R is 4 kilo ohm, R2 will be 32 kilo ohm. Okay. And you can also find the exact frequency here. 1 by 2 pi RC root 3. If you substitute the value of R and C, it will be 2.3 kilohertz. Okay. That will be the answer. Next problem. For the Schmidt trigger circuit shown in the figure, assume RA equal to 10 kilo ohm, RB equal to 20, R1 5 kilo ohm, R2 20 kilo ohm, V reference 2 volt, and the saturated output voltages are plus minus 10 volt. We need to find UTP and LTP. So first of all, let me derive the positive voltage. Positive terminal voltage by voltage division is V0 into R1 by R1 plus R2. So V0 into 5 by 5 plus 20. That is V0 by 5. To find negative terminal voltage, what I will do? I will apply superposition. Because now there are two sources, input voltage and reference voltage. So first consider reference voltage to be 0. In that case, V minus will be Vi RB over RA plus RB. In next case, consider input voltage to be 0. In that case, V negative will be V reference RA over RA plus RB. How I am applying voltage division? Because the input current to op amp is 0 ampere. So these two resistances are in series. Now if you plug in the value of V reference RA and RB, RB is 20, RA is 10. So Vi by 3 plus 2 into 10 by, 2 Vi by 3, 2 into 10 by 30. So 2 by 3 Vi plus 1. That is V negative. Now, if V0 is actually equal to 10 volt, then V positive is how much? V0 by 5, which will be 2 volt. So, if I say V negative is greater than V positive, in that case V0 will become minus 10. 2 by 3 Vi plus 1 is equal to 2. So Vi plus 1 is equal to 3, or you can say Vi is 2 volt. That is your UTP, because here I have taken V0 equal to Vset. Okay. So you will say that, or you can apply here greater than equal to 2, greater than equal to 3. So you will say that when Vi goes above 2 volt, output will switch from plus 10 to minus 10. Now if V0 is minus 10 volt, then V positive, which is V0 by 5, is minus 2 volt. So if we say V negative less than equal to V positive, V0 will be switching to plus 10. So 2 by 3 Vi plus 1 less than equal to minus 2. This will get cancelled. Vi plus 1 less than equal to minus 3, which means Vi will be less than equal to minus 4. That will be LTP. So if Vi tries to go below minus 4, V0 will switch from minus 10 to plus 10. If Vi goes from plus 10 to if Vi goes above 2 volt, V0 will go from plus 10 to minus 10. So UTP is 2 volt and LTP is minus 4 volt, which means hysteresis width, which is difference of UTP and LTP, will be 6 volt. Okay. So that is how you can solve any problem based on Schmidt trigger, by equating negative terminal voltage to the positive terminal voltage. So such kind of question can be asked in GATE exam based on oscillator. So this is all from this lecture, and we'll continue in the next one. Thank you. Hi guys, in the previous few videos we have discussed all about the different kind of oscillators. Oscillators were made using op-amps such as Schmidt trigger, stable multivibrator, monostable multivibrator, and using BJT and FET also, like RC phase shift oscillator, Hartley oscillator, Colpit oscillator. In this lecture we will discuss a special IC or an integrated circuit that is basically used to implement multivibrator, and that IC is called as 555 timer IC. It is a dedicated circuit. It is a circuit which is built into a integrated circuit and is specifically designed for the purpose of implementing a multivibrator. That is, you don't need op-amp, BJT, all these active devices. Just this IC is sufficient to make two type of multivibrator, majorly monostable and astable. Okay. So what is the meaning of this 555 timer IC? The name is derived from 3 5 kilo ohm resistors inbuilt in the IC for voltage division. Inside this IC we have 3 resistances, each of 5 kilo ohm, and they are used to implement voltage division, and hence it is called as 555 timer. Now this 555 timer IC is a 8-pin IC. Okay. So we show ICs like this. It is a 8-pin IC. 1, 2, 3, 4, 5, 6, 7, 8. It has 8 pins. Pin number 1 is kept as ground terminal. Okay. Pin number 2 is your trigger terminal. Pin number 3 is your output terminal. Pin number 4 is your reset terminal. Pin number 5 is your control terminal. Pin number 6 is your threshold terminal. Pin number 7 is discharge terminal. and pin number 8 is your supply terminal, where you will give the power supply VCC. Okay, but before studying this 555 timer IC, the basic concept of flip-flop must be clear, because when we are constructing this IC, we are making use of a flip-flop inside the IC. Okay, so let us see the construction. If you see the construction, this box is basically representing a 555 timer IC. Okay, now see, what happens actually is, there are two comparators in the circuit, and these are the 3 5 kilo ohm resistor, due to which we are giving it the name as 555 timer IC. This node is connected to inverting terminal of comparator 1, and this is connected to non-inverting terminal of comparator 1. This is pin number 8 supply, this is pin number 1 ground. Threshold is connected to positive terminal or non-inverting terminal of comparator 1. Trigger is connected to inverting terminal of comparator 2. And control voltage, which is only sometimes used, is connected to inverting terminal of comparator 1. This is a SR flip-flop, in which this is R input, this is S input, this is reset bar. Okay, reset bar means reset is active low input. That is, reset is active when it is 0. Active low means it becomes active when it becomes 0. Are you getting my point? So when you make this input 0, when you make pin 4 equal to 0, then flip-flop is reset. Okay, we actually reset the flip-flop when we make pin 4 equal to 0. Is it fine? Being reset means Q will become 0 and Q bar will become 1. That is the meaning of reset. So you can reset the flip-flop. Now this is Q bar, and after that we have applied an inverter to take the output. So if you are applying an inverter at Q bar, output will be equal to Q. Are you getting my point? All the pins are clear. So reset is being used to reset or clear the flip-flop. I'll tell you the meaning of discharge later on. So let us understand the working pin by pin. So pin number 1. Pin number 1 is ground. So this pin is actually connected to ground. How you will connect it to ground? By ground I don't mean earth. See, whenever you are running a IC, you will give it a DC supply. DC supply always has two terminals, positive terminal and negative terminal. So what we do is connect positive terminal of supply to pin 8 and negative terminal of supply to pin 1. That way, what I am essentially doing is I am connecting a DC source like this. Like this. Okay. So that is how you don't need to apply ground separately, but you will connect a DC source between VCC and the ground. Is my point clear? Okay. Moving on. Now see, due to voltage division, the total voltage is VCC. This is the total voltage, and 3 5 kilo ohm resistances are connected. So this voltage will be equally divided in the 3 resistances. Each resistance will have a voltage of VCC by 3, which means the negative voltage of comparator 1 will be 2 VCC by 3, and positive voltage of comparator 2 will be VCC by 3. Okay. So moving on to the next pin, that is pin number 2. Pin number 2 is your trigger terminal. Okay, it is your trigger terminal. Now see, trigger terminal is connected in comparator to where the positive voltage is 1 by 3 VCC. So if V trigger becomes less than VCC by 3, that means at the trigger input you will apply a decreasing pulse like this, and as soon as it crosses VCC by 3, V negative will become less than V positive. See, positive voltage is VCC by 3. If trigger input on negative terminal voltage is less than VCC by 3, the output of comparator will be Vset, or you can say high. If the output of this comparator is high, S input of the flip-flop is high. If S becomes 1, the output of the flip-flop also becomes 1. This is called as set input. So whenever S is 1, the output becomes 1 and Q bar becomes 0. Moving on to the third pin, pin number 3. Pin number 3 is your output terminal. So at output terminal we connect the load. Now this load can be connected in two ways, that is between pin 3 and ground, or between pin 3 and VCC. If you connect between pin 3 and ground, it is called as off load. Between pin 3 and VCC, it is called as on load. So you don't have to do anything, you just have to connect the load at pin number 3. Pin number 4. Pin number 4 is your reset terminal. Okay. If it is your reset terminal, we will say when pin 4 is 0, flip-flop is reset, and when flip-flop is reset, the output Q will become 0. So pin 4 is basically used to reset the output. Okay. Now pin 5. Pin 5 is your control terminal. Generally the voltage at this terminal, as you can see, is 2 by 3 VCC. But you can apply a different voltage by means of the control voltage. So that means we can change negative voltage of comparator 1 to change pulse width. How you can change pulse width we will understand when we will talk about monostable multivibrator, but this pin will be very rarely used. You just have to remember it will be used to change the pulse width of the output. Pin number 6 is your threshold terminal. Okay. Now it is connected to positive terminal of comparator 1. The negative terminal of 1 is connected to 2 by 3 VCC and positive terminal is threshold. Now when you will say positive voltage is greater than negative voltage, the output of comparator will be Vset or high. Now this output is connected to R in the flip-flop. R is called as reset. So when R is 1, output will become low. So in order to make the output low, you have to apply voltage more than 2 by 3 VCC at threshold. In order to make the output 1, you have to apply voltage less than 1 by 3 VCC at trigger. Remember these two things. If you apply voltage more than 2 by 3 VCC at threshold, output will become 0. If you apply voltage less than 1 by 3 VCC at trigger, output will become 0. Sorry, output will become 1. Okay. Then in the next case, pin number 7. 1 minute. If you are not able to understand it, see this. Actually threshold is connected at positive. That is my mistake. This is actually positive. This is actually negative. Okay. So when you will apply a voltage more than 2 by 3 VCC, actually this is positive threshold. Yeah, right. This is negative 2 by 3 VCC. So when V threshold is greater than 2 by 3 VCC, then you can say output becomes 0. And if V trigger is less than 1 by 3 VCC, output becomes 1. So that is how you can change the output from 1 to 0 or from 0 to 1. Pin number 7. Now this pin number 7 is called as discharge terminal. If you see, this discharge terminal is connected to Q bar. So when Q bar is high, this BJT will be on. If this BJT is on, it will help us discharge the load capacitance. Okay. So that means in discharge terminal, when Q bar is 1 or Q is 0, then BJT turns on, which means VCE almost becomes 0, or you can say collector is connected to ground. If collector gets connected to ground, then capacitance between collector and ground basically discharges. So that is why it is called as it is called as discharge terminal. And pin 8 is the supply terminal. I told you we connect a DC source between pin 8 and pin 0. Most importantly, you just have to remember these two things about trigger and the threshold. Okay, remember these two things. So let us see the first application, that is monostable multi vibrator. Remember the pin name. Pin number 4 is what? Reset. 2 is what? Trigger. 6 is what? 6 is your which terminal? Threshold. Okay. 7 discharge. 1 is ground, 8 is supply. See, we have connected pin 4 and 8 to VCC. Why? I told you reset is active low. So that means when reset is 0, flip-flop Q becomes 0. So if you want to operate the flip-flop and you want to operate the IC, then you have to keep reset equal to 1. If you keep reset as 0, the IC will be reset. We don't want that to happen. We want the IC to work. For that, reset is connected to VCC or high. That means here reset is actually 1. Is this fine? 8 is the supply pin connected to VCC. 1 is the ground pin connected to ground. 5 is the 3 is the output pin. Okay, 3 is the output pin and 5 is the control terminal, which is connected to a capacitor and ground. So we are not applying any voltage at control terminal. We can apply the voltage, but that is to change the pulse width. Right now we are not applying any voltage. See here, the trigger and the threshold terminal are connected together. Both are connected together. I told you, if trigger voltage becomes less than VCC by 3, output becomes 1. And if threshold voltage becomes greater than 2 by 3 VCC, then output becomes 0. Now what will happen? What will happen is, initially, suppose Q is 0. Initially, Q is 0. If initially Q is 0, then what will happen? The circuit is stable. Okay. Now if you want to make Q equal to 1, you have to apply a trigger input at terminal 2. So if trigger is applied at 2, that is a decreasing pulse is connected at 2. So when V2 becomes less than 1 by 3 VCC, output will become 1. So that is by applying a trigger input, we have sent the output from the stable state to the unstable state. So when the output becomes 1, this capacitor will start to charge through R1. C charges through R1. See, till the output is 0, I have just now told you about discharge pin. When the output is 0, capacitor discharges. That means till the output is 0, the voltage of this capacitor is discharged, or its voltage is 0. So now we have applied a decreasing pulse to make the output 1. So discharge is inactive. Why inactive? Because the output is 1 and discharge is only active at output equal to 0. Are you getting my point? So here discharge will not work because output is 1. Discharge only works when output is 0. So initially output was 0. So discharge pin was working, and if discharge pin is working, this capacitor is connected between discharge and ground. So capacitor is discharged. Are you getting my point? See this? It is connected between 7 and ground. So if discharge pin is connected or discharge pin is active, capacitor will be discharged. Now once you have made the output 1, discharge is inactive. So capacitor will charge through R1. Okay. So up to what it will try to charge? It will try to charge up to VCC. What is the initial voltage? Capacitor was discharged, so 0. So how you will write VCT? VC infinity plus VC 0 minus infinity e to the power minus t by tau. So VCC 1 minus e to the power minus t by R1C. Now this VC is actually equal to V2 equal to V6. Now if V6 equal to VC becomes greater than 2 by 3 VCC, then output will again become 0. This is your threshold pin. At threshold pin, if you apply a voltage greater than 2 by 3 VCC, output will go back to stable state. So let me equate the capacitor voltage to 2 by 3 VCC. Okay. So now this gets cancelled. So 1 by 3 equal to e to the power minus t by R1C. So time is R1C ln 3. That means after this time, output again comes back to 0. Output again becomes 0. If output again becomes 0, so output again becomes stable. So that will be your pulse width. If you wanted to change the pulse width, what you would have done? You would have applied a control voltage, and then you will not be comparing it with 2 by 3 VCC. You will be comparing it with the control voltage. Okay, because just see the block diagram. Let me show you again the block diagram. If here you apply control voltage, then the voltage of threshold must be crossing the control voltage to make reset equal to 1. Okay. So that means you can control at which voltage switching will occur by applying a control voltage. Now once output becomes 0, this discharge pin will activate. If discharge pin is activated, capacitor will discharge. So discharge gets activated. So capacitor discharges to ground. Okay. So capacitor voltage again becomes 0. So when output is 0, the discharge pin becomes activated. Moving on to the next application is the astable multivibrator. Again remember the pin name. 2 is trigger, 6 is threshold, 7 is discharge. Again, like previous circuit, the reset pin is connected to VCC. So reset is inactive, and when reset is inactive, IC can work. If you make reset as 0, the output of IC will be 0. Now see, the trigger and the threshold pin are directly connected to capacitor. One is connected to ground. Control terminal is connected to a capacitor C dash. 3 is output. But now discharge. Earlier see, discharge was also directly connected to capacitor. But now between discharge and capacitor, we have another resistance R2. So what happens? Initially assume VC equal to 0. If VC is 0, the trigger voltage, which is VC, is less than VCC by 3. If it is less than VCC by 3, the output of comparator 1 will be high. That means S is equal to 1 and output becomes 1. If output becomes 1, the discharge pin is inactive. Discharge pin can only work when output is 0. So capacitor charges. Capacitor charges through R1 and R2. And when VC is also equal to V6, becomes greater than 2 by 3 VCC, the R input becomes high, so output again becomes 0. Okay. So when output becomes 0, discharge pin is activated. If discharge pin is activated, capacitor will discharge. Now when capacitor will discharge, between discharge pin and ground, we have a resistance R2. So capacitor discharges through R2. That means capacitor is charging through R1 and R2 and it is discharging through R2. And when capacitor is discharging, as soon as VC equal to V2 becomes less than VCC by 3, S will become 1 and output will again become 1. Okay. So that way output will keep on oscillating between 1 and 0 and capacitor voltage will oscillate between 2 by 3 VCC and 1 by 3 VCC. So let me show you this by means of a waveform. So this is VC and this is V0. So initially capacitor is discharged. So its voltage starts from 0 and it charges exponentially through R1 and R2. Now as soon as its voltage becomes 2 by 3 VCC, initially output was 1, the output becomes 0. Now the capacitor will discharge, and as soon as its voltage becomes VCC by 3, the output will again become 1. So capacitor will again charge. Now as soon as output becomes VC becomes 2 by 3 VCC, output will again become 0. So this is the time period of oscillation. Okay. So remember, charging is through both the resistance R1 and R2 and discharging is only through R2. Now first let us talk about discharging. During discharging, What is the initial voltage? This is the discharging period. Initial voltage is 2 by 3 VCC. Capacitor will want to fully discharge, so steady state voltage is 0. So what is VCT? Infinity plus 0 minus infinity e to the power minus t by tau. Don't think that steady state voltage is VCC by 3. It wanted to discharge to 0, but it stopped at VCC by 3. So I want to know this duration T1. So I'll say at t equal to T1, Vc equal to VCC by 3, and at this point discharging stops. Okay. So VCC by 3 equal to 2 by 3 VCC e to the power minus t by tau, or instead of t you can now write T1. So T1 will come out to be tau ln 2, or you can say R1 plus R2 C ln, R2C, because discharging was only through R2. So R2C ln 2. If it is discharging through R2, then the time constant is R2 into C. Okay. Now let us talk about charging. Charging is this interval. Now why I am not taking initial one? Because initially capacitor voltage started from 0. But now it will keep on oscillating between 1 by 3 VCC and 2 by 3 VCC like this. Okay. So that means this period will be called as transient, but we are more interested in steady state. So during charging, what is the initial capacitor voltage? VCC by 3, and capacitor wants to charge up to VCC. So what I'll say about VC, steady state voltage plus 0 minus steady state. Okay. Initial is actually VCC by 3 only. So it is VCC by 3 e to the power minus t by tau. Here, since it is charging through both R1 and R2, the time constant is R1 plus R2 into C. VCC minus 2 by 3 VCC e to the power minus t by tau. Now I will say at t equal to T2, Vc equal to VCC by 3, 2 VCC by 3, and charging stops. So 2 by 3 VCC is VCC minus 2 by 3 VCC e to the power, instead of t now what we will use? T2. From here if you find T2, it will be R1 plus R2C ln 2. So we have found out both the periods. The total time period is T1 plus T2, which will be R2C ln 2 plus R1 plus R2C ln 2. C ln 2 can be taken common. So R1 plus 2 R2 C ln 2. What about duty cycle? The output is high. The output is high during T2. So duty cycle delta is T2 by T. That is R1 plus R2 over R1 plus 2R2. That is the duty cycle of the output. So that is how your astable multivibrator will work. So if I summarize, what you have to remember, that pin 2 is your trigger terminal, and whenever V2 is less than VCC by 3, output becomes 1. Pin 6 is your threshold terminal, and whenever V6 is greater than 2 by 3 VCC, output becomes 0. Then in monostable multivibrator, the pulse width was RC ln3. In R stable, the time period is R1 plus 2 R2 C ln2 and duty cycle is R1 plus R2 by R1 plus 2 R2. And how to identify R1 and R2? R2 is discharging resistance between pin 7 and C. So if you remember this much in 555 timer IC, you can solve all the problems. Most of the problems are formula based only. You don't have to apply the working concept of the 555 timer IC. So this is all from this lecture. In the next one, we'll solve some problems based on 555 timer. Thank you. Hi guys, in the previous video I told to you about the operation of 555 timer IC. We saw the construction as well as we saw two applications of 555 timer IC, that is in the construction of monostable multivibrator and the astable multivibrator. In this video I'll show you some problems that are based on 555 timer IC. Okay, so see the first one. An IC 555 chip has been used to construct a pulse generator. Typical pin connection with component is shown below. However, it is desired to generate a square pulse. Evaluate RA, RB if the C has the value for the configuration modification in the external circuit configuration. Okay. Now let us understand. If we are generating a square pulse, that means we are operating it as astable multivibrator. In astable multivibrator, we derived time period was R1 plus 2 R2 C ln2 and duty cycle was R1 plus R2 by R1 plus 2 R2. Okay. Now, if you see here, instead of R1 R2, we have RA, RB and C. Now what is the on period? The on period we derived was RA plus RB C ln2 and discharging, that is off period, was RBC ln2. Now we need a square pulse and duty cycle is not given. So what I will assume? I will assume that duty cycle is 50%. But in that case, T on has to be equal to T off. In 50% duty cycle, for half the time output will be on and for the half time it will be off. But from the formula we can say T on is not equal to T off. That means it cannot generate a square pulse. And that is why it is saying we have to modify the external circuit. So what modification I do is, I connect a diode here. Why do I connect a diode? That is, during capacitor charging. During capacitor charging, when current is flowing into the capacitor, the current will flow through the diode into the capacitor. That way RB will be bypassed. So what is the time constant during charging in that case? RA into C. So on time will become RAC ln2. And during discharging, current should leave the capacitor. If current tries to leave the capacitor, the diode will be off. Because diode cannot conduct from cathode to anode. It can only conduct from anode to cathode. So diode will be off. That means discharging will occur through RB. And off time will be RBC ln 2. Now both time can be equal if RA equal to RB. So the total time period in this case will be RA plus RBC ln 2, or you can say 2RC ln 2, and frequency will be 1 by 2RC ln 2 should be equal to 10 kilohertz. From here, if you find out the value of R, it will be 7.14 kilo, which is equal to RA and also equal to RB. If it had given us a value of duty cycle, then from duty cycle we can calculate the relation between R1 and R2, and based on that duty cycle and time period, we can find RA and RB. But remember, a stable multivibrator using 555 timer can never give 50% duty cycle. So for 50% duty cycle, we have to bypass RB or R2. Moving to the second problem, implement a monostable multivibrator using the timer circuit shown. And we also have to derive an expression for on time or pulse width. There is a small mistake in this problem. This must be R and this must be S. Now see, here instead of using 55 kilo ohm resistor, we have changed the resistor to R, R by 2 and R. Now when you apply voltage division, what is the voltage here? V2 positive. What is the voltage here? VCC into R over R plus R by 2 plus R. That is 5R by 2. 2 VCC by 5. What is the voltage at the negative terminal of comparator 1? Again by voltage division, VCC into R by 2 plus R by R plus R by 2 plus R. That is 3 by 5 VCC. Okay. These are the two voltages. Now see, initially suppose output is 0. If output is 0, this discharge pin is activated. So how will I connect externally the components? This is pin number 7, 6, 2, 4, 8. 4 and 8, the supply is connected to VCC. Okay. Then we connect capacitor between 7, 6, 2 and ground. Ground pin is 1. And the control pin is connected via capacitor to ground. This is the output pin. Okay, that is the connection. So now if you see, if the output is 0, discharge pin is active and VC is 0. Now, if a trigger is applied, now we are applying a trigger, that is we are making V2 minus, that is the trigger voltage, less than 2 VCC by 5. In that case, positive voltage is less than negative voltage, output will be high and S will become equal to 1. If output is high, S will become equal to 1 and output Q will be 1. If Q becomes 1, discharge is inactive. If the discharge is inactive, C charges through R. Okay. If C charges through R, then since VC is also equal to V6, when it becomes more than 3 by 5 VCC, Then in comparator 2, see, in comparator 2, if threshold voltage, comparator 1, in threshold voltage V1 plus becomes greater than V1 minus, which will make R equal to 1. If R is 1, output will again go back to 0. So capacitor, when it is charging through R, initial voltage is 0 and it will try to charge up to VCC. So what is VCT? VCC 1 minus e to the power minus t by tau. So we want it to reach up to 3 by 5 VCC, which means t is tau ln 5 by 2 or RC ln 2.5. So that is the on time of the monostable multivibrator. After this time, the output will again become 0. Is it fine? Moving to the next problem. An astable multivibrator circuit using 555 timer is shown below. We need to find the variation of capacitor voltage. If it is a standard 555 timer, that means internally we have 3 5 kilo ohm resistances. If we have 3 5 kilo ohm resistances, what is the voltage of pin 6? 9 into 2 by 3, it is 2 by 3 VCC, it is 6 volt. What is the voltage of pin 2? It is VCC by 3, that is 3 volt. Okay, these are the voltages fixed due to internal 5 kilo ohm resistor. Now if you see, capacitor is directly connected to trigger. So V2 equal to Vc. If it goes below 1 by 3 VCC or 3 volt, then output becomes 1. So what is the minimum value of capacitor voltage? 3 volt. And in order to make the output 0, V6 should go above. V6 should go above 6 volt. In that case, output will be 0. So when this voltage is 6 volt, I want to know the value of Vc. This is 6, this is 3. What is the current I? I current is actually how much? 6 minus 3, or 1 minute. We want to know this terminal voltage. When the terminal 6 voltage is 6 volt, I want to know Vc. So what is this current I? I is how much? I is actually 9 minus 6 by 30k. So 0.1 milliampere. Current cannot enter op amp, so the same current will go ahead. So what is Vc by KVL? 6 minus I into 10k. 6 minus 1 equal to 5 volt. So that is the maximum capacitor voltage, that is 5 volt. Answer will be A. Don't directly mark that capacitor voltage will oscillate between 3 and 6. Why? Because capacitor is not directly connected to pin number 6. There is a resistance which will cause voltage drop. So capacitor voltage cannot reach 6 volt. It will be less than 6 due to voltage drop in the 10 kilo ohm resistor. Moving to the last problem, it is saying in astable multivibrator circuit, we need to find the frequency of oscillation. So the formula that we studied for time period was Ra plus 2Rb. Rb is the resistance between 7 discharge and capacitor. C ln 2. So what is the frequency? 1 by Ra plus 2Rb C ln 2. Ra is 2.2 kilo ohm plus 2 into 4.7 into 10 to the power 3. 0.02 to 10 to the power minus 6 into ln 2. So this frequency will come out to be 5.65 kilohertz. So this question is directly formula based. We can find the frequency of oscillation of the multi-vibrator or astable multi-vibrator. So we can see there are two type of problem. in which we do small modification in the circuit and in which we are directly using the formula and the circuit of the 555 timer IC. The questions from this topic are rarely asked, but they are very much formula based. So before going into gate examination, just before gate exam, just revise this topic, but it does not need regular revision. So no need to revise it again and again. One revision would be sufficient just before the gate exam. So that is all from this video based on questions of 555 timer. Thank you.